and the plant is at Guinea Filaments Limited. So I welcome you to the session, sir. Now I request the session chair to handle over the session. Over to you, sir.
Yeah, thanks, Bipula, and good morning to all respected dignitaries, highly qualified and experienced and knowledgeable speakers, and my dear audience. I hope I am audible and visible as well.
Yes, sir, you're audible and visible.
Yeah, thanks. So I'm highly honored to chair this great session on innovation in non-woven technology. So let me introduce myself. So I'm Ayan Chakravarti, as Bipul has already mentioned. So I'm MTech in Textile Technology and having around 29 years of experience in various industries of repute like Bardhaman, Guinea Filaments, and worked in many areas of textile like in spinning, knitting, non-woven, and nowadays I'm working in FMCG, that is the converted product of spunless non-woven. So when we were in college, non-woven was just introduced in syllabus. Now India is moving ahead quite good in non-woven. And I remember we started this non-woven plant, our spunless non-woven technology, in 2007. And nowadays, many technologies have come in India in spunless, in spun bond, in SMMS, and also in needle punch and other areas as well. Big investment has happened, and similarly in converted products as well. Many investment has happened and is also happening very rapidly. COVID has shown the world that what India can do. So India become nowadays a hub of hygiene product. Now coming back to this today's session, so we have 5 speakers with their diverse subjects. So I request all speakers to finish within the allocated time, and after every paper we can take a few questions if time permits. And the topics actually are very interesting. So it is covering right from filtration to energy solution in sustainable manner, then electroconductive polyester fabric for e-textile. I think it will solve some problem of static related safety, and also fascinated to see one topics regarding antimicrobial fabric that they are using with the flower that we were used to use in our puja ghar. So that's great, and also also a paper on moisture management in fabric. So now let me introduce our first speaker today, that is Professor Apurva Das. Actually, I know Apurva personally. He is my senior, and he is professor in IIT Delhi in Department of Textile and Fiber Engineering and Institute's chair professor. He has joined IIT Delhi in 2002 as a faculty after serving in the textile industry and in research organization for about 11 years. His main area of teaching and research interest are clothing comfort, sports textile, non-woven and technical textile, protective textile, filter fabric, geotextile, medical bandage, textile composites, and instrumentation. I think Apurboda, it's a big sphere that you have worked in. He is the recipient of Teaching Excellent Awards. He has international research collaboration with universities from different countries like Germany, Poland, Hungary, Slovenia, Italy, Portugal, China, South Korea, UK, Hong Kong, Croatia. He has published many research papers in journal and conference, authored and edited several books, monographs, and written chapters in books. So, welcome Apurboda. Now the stage is yours.
And thanks, Ayan, and for nice introduction. Without any delay, as I are already late, so I will try to start. Okay. So I'll just share the slide. Is my slide visible to everyone?
Yes.
Yes. Okay. Let me start. Okay. Thanks, Mr. Ayan Chakraborty, and thanks the organizing team for giving the opportunity to present our work. So this work is actually outcome of one PhD student, Mr. Rahul Gadkari, and other authors are there. So I'll be talking on sustainable water purification system from non-woven fabric and bioactive nanomaterials. This is actually for rural people with where we don't have any power supply, or it's with a cheap solution we try to develop, okay, and using the bioactive nanomaterials. So if you see which motivates us to work in this area, because if you can see that most of the people actually in a rural area, throughout the world, rural area, actually they drink the surface water, and which actually generates results different types of disease. You can see, so more than maybe 263 million people spends more than 30 minutes per day to bring the water to their home. And you will see that more than 844 million people, as per the UNICEF data, they don't have the access to for drinking water. You can see the people are actually forced to drink the surface water. That's the main problem as far as drinking water is concerned, and it's basically in the rural area, particularly it's prominent in the developing and underdeveloped country. Even in India, we have a severe problem of drinking water. As per WHO, 1.8 million deaths are per year. It's due to the drinking water, basically. And you can see in 2018 data, 7 deaths per day is mainly due to drinking of polluted water. So this is the basic problems we are facing, particularly our rural people are facing. So the challenges are that there we have solutions. Okay, we have different solutions which our rural people, poor people, they can't actually afford to have all this type of the water filtration system at their home. So due to the extreme poverty and limited electricity, high capital investment, high operational cost, So, and absence of skillful labor. These are the main challenges we were before we develop. We have taken care of this, all these challenges. So the issue in front of us was that we had the desirable thing which we thought of. It should involve low level of mechanisms. So that means anyone can, untrained, unskilled person can actually run this system. It should involve a low level of complexity. Very simple system should be there, and no electrical power is required. These are the basic requirement for our development. This project was sponsored by ministry. So what we thought, as it has already been mentioned, that nonwoven is basically is a technology which is grown, which is actually, as far as Indian perspective is concerned, it's basically established technology, and needle punch is one of the simplest technology, and which is totally available in India. So we thought that let us go with the non-oven based filtration. So needle punch we have taken initially, and then we thought two-stage filtrations are there. One is the based on the needle punched fabric. Then to remove the bacteria, to kill the bacteria, we have used the nano science. Okay, nanoscale science and engineering we have incorporated in the filter. Okay, and that is the silver nanoparticle we have used, and as per as WHO guidelines, the silver leaching should not be, content should not be more than 0.1 ppm. Okay, so that outline for my presentation is that what we have done, as I have mentioned, two-stage filtration. One is first is the first stage filtration, where we try to remove the suspended solids and turbidity. So this is the first, and mind that it should be without any power. Okay, and then in the next stage, what we have done, we have tried to incorporate the nanotechnology. So the polyester silver impregnated, silver nanoparticle impregnated polyester fibers are available. So we have tried, we have used that this fiber in the non-woven fabric manufacturing. Then development of electrospun nanofibrous material. So after preparing the non-woven fabric, we have actually used the electrospun nanofibrous membrane on the non-woven substrate. Okay, and design and development of prototype of water purification system. These are the stages we have covered. So first thing is that removal of suspended solids and turbidity, the larger particles we wanted to remove. And here we have used the wicking characteristics of non-woven fabrics. So if suppose at the bottom, it's water is there, turbid water is there, and when the water flows against the gravity, so it will actually resist all these larger solid particles. So that way, in the first stage, against the gravity and using the wicking characteristics of non-woven, we have tried to remove the turbidity. So we have done some experimental plan. I am not going in depth in all this. So we have varied the needle density and depth of penetration. And finally, see, this is the system. It's the first stage filtration. Okay, first stage filtration, where this is the turbid water. So this is the synthetic turbid water we have used, where it's with synthetic clay we have taken, And then this, you can see it's a non-woven fabric sample. And against the gravity, when it's wicked, and we are getting the water here at the after first stage filtered water, simple by flowing the water through along its length, we could actually achieve around 90%, more than 90% of the turbidity clearance. You can see water flow rate is actually, it's dependent on fiber shape factor. We have changed the fiber shape factor, and also needle density. As the fiber shape factor increases, it's well known, the water flow wicking rate increases, and depth of needle density as it increases due to the size of the capillary, also water flow increases. So these are the different experimental studies on the water flow rate. And also you will see the turbidity removal efficiency we could achieve typically 99%, more than 99%. The turbidity is cleaned, actually removed, due to this anti-gravity. Actually, that's against the gravity when the water is flowing. So it is actually water is flowing using the this wicking phenomena, but the dust particle, that particles, suspended particles, are actually arrested. So these are the different studies, and finally we could optimize the values. What we have optimized using the fiber shape factor 1.3, needle depth, punch density is 180, and depth of penetration. This is the first stage filtration, and this parameters we have used in further study. Okay, I'll not, that we have already done. Now in second stage, what we have done, we have used this same parameter, and then we have taken the silver nanoparticle embedded polyester. Okay, so here we have configured the unique antibacterial needle punched non-woven. So we have removed the solid particle. Now our focus was to remove the kill the bacteria, okay, using the silver nanoparticles. Okay, so this the silver nanoparticle is very well known. I am as a antibacterial agent, so I am not going in depth. So what we are trying, so what we have observed, this is the normal polyester silver nanoparticle fiber, where you will see the most of the nanoparticles are actually at the surface or inside the structure. Though we have to actually expose this nanoparticle to the surface so that it is very much active. So what we have done, hydrolysis, alkaline hydrolysis process we have used. You can see the hydrolyzed nanoparticle, it is exposed, and which is active for the killing of bacteria. Okay. Now the process is here. You can see that untreated non-woven fabric. So non-woven fabric, we have treated the non-woven fabric. So this is the untreated, and then we have hydrolyzed. So different stages are there. So once we hydrolyze this non-woven, you will see the fibers are actually, the nanoparticles are exposed here. So if you compare, this is the large number of nanoparticles are exposed on the surface, and this is actually improving the antibacterial effect. So you can see these are the different study which shows that the etching out of the this nanoparticles, okay, at the surface. You can see here. And now if you see the surface morphology, this is without alkali treatment, untreated silver nanoparticle. At the surface, very less number of nanoparticles are present. And if we see the treated paper, you can see due to this etching out, the nanoparticles are visible at the surface. And that resulted the improvement. This is the pure without any silver nanoparticle, and with silver nanoparticle without before the hydrolysis. After hydrolysis, you can see there is an improvement of antibacterial activity. Okay. And then what we have done, this is the fabric, polyester based fabric. Then what we have tried to develop the electrospun nanofibrous membrane on non-woven structure. So the non-woven structure we have developed already. This is the non-woven structure with the hydrolyzed surface, and on that surface we have developed the electrospun nanofibrous membrane to enhance the filtration efficiency. And here there are different technologies available. We have used the electrospinning because of different advantages of electrospinning technology. And then the problem statements were the poor electroconductivity of the chitosan. We have used the chitosan, as chitosan is known to be the natural product, natural antibacterial product. So that's how it is a poor electrospinability. So that's to improve the electrospinability. We have blended is to with the polylactic acid. So at different proportion we have used. So 100% polylactic acid, then 50-50, 70-30. What we have observed, so you can see as the chitosan content is increasing, so you will see the diameter of fiber diameter produced is reducing. So 70-30 chitosan and PLA, which is giving the minimum diameter 131 nanometer, which we have we could develop. So that we have used this fiber. We have actually this electrospinning we have actually embedded on the developed on the substrate, polyester substrate. Okay, and this is showing this FTIR is showing that it's a combination of PLA and chitosan. Now, after that, what we have done? So here, these are the different combinations, different proportion of oxygen, carbon, and nitrogen, which shows that it's a mixture, proper blend of chitosan and PLA. Now, then we have tried to actually synthesize that silver nanowire on this nanofiber. Inside the nanofiber, we have actually this is the chitosan PLA nanofiber, and inside the nanofiber we have developed the silver nanowire, so that to improve the antibacterial activity further. So the silver nanowire we have there are standard methods to develop the silver nanowire. We have actually optimized it in the laboratory, and you can see these are the silver nanowire. So with the length ranging from 7 to 12 micron and diameter around 50 micron, okay, 50 nanometer. So this 50 nanometer, this silver nanowire is embedded inside the nanofiber. So you can see this is then we have used this 0.5%, 1%, 3%, and 5% nanowire we have mixed with the chitosan and PLA. This we have mixed here. This is the nanofiber and nanowire we have mixed here with this proportion. You can see that what we could develop, we could arrange to produce. This is the nanofiber, and within this, inside this nanofiber, there is a silver nanowire, which actually enhance the antibacterial activity. And this.
To interrupt, Apurva, can you please make it faster?
Okay, it's okay. Now this nanowire, which we have this nanofiber, nanowave, we could, you can see, we could achieve up to 100% of antibacterial activity. So this nanowire we have actually developed, nanowave we have developed on the nonwoven fabric, needle punch nonwoven fabric. So you can see this is the needle punch nonwoven fabric, and then another layer of the nanowire. So multi-layered nonwoven structure we have developed. Then we could develop the cartridge, and this cartridge can be used in the on this, with this, using this cartridge we could develop, we could use the second stage filtration. Now these are the cartridges we have used, and here you will see we don't need any water, any power. You have to fill the water here. And first stage, these are the nonwoven fabric of needle punch nonwoven fabric for wicking characteristics, first stage filtration, and then water will be stored at this point, and in the second stage there will be a filtration using the gravity, okay, here, and then you will get the clean portable water. So second stage filtration and final storage you can take. Only thing, you have to lift water here using bucket. You can just fill the water, and this is the system which we have developed here and which we have patented this system. And you can see the small animation here. You just see the, you just fill the water here, and first stage filtration will be there. Then the water is coming out, and you can see. And what we have observed, the cost of cleaning is, it's basically typically 0.1 paisa, it's a per liter. It's a typical costing is there. In 10 liter, you will actually 1 paisa will be required, and this can be installed in rural place. We are in a process to optimize, and I think that's all about my talk. Yeah. Okay. Thank you.
Thank you, Apurvo sir. It was excellent, and as if I was sitting in your class. So it was very exciting, and to know that you are doing some problem-solving initiative for rural and poor people, and giving them potable water. That's a great initiative, and wish all the success to you as well as the team.
Okay.
Now our next speaker is Professor Wazid Ali. So Professor
I think,
Wazid,
hope I was not late. Basically, we started at 11:07, and it was okay.
yeah,
Okay.
yes,
Anyway.
yes. So anyway,
And Professor, one thing, Professor Wajid Ali is also the part of this innovation, this team, basically.
oh, that's great. That's great.
Thanks.
And until now, I have not received any question. Although I have many questions. So
we
let's
can
see
discuss
if
with
at
them.
the end of the session we have
Yeah.
time, then we will discuss about this. And all the audiences are requested to put their question in the chat box. If there is any question, we can take it later. So now let me introduce Professor Wazid Ali, who is the next speaker. So he is a professor in Department of Textile and Fiber Engineering at IIT Delhi. He has been awarded the prestigious Commonwealth Split Site Doctoral Fellowship 2008 for the Commonwealth Fellowship Commission, London, to pursue 1 year research work in the UK during his PhD studies. He was the recipient of the Bolton Fellowship from the University of Bolton, UK, for 3 year PhD program at IIT Delhi. He has published several research papers in different international peer-reviewed journals. He is a lifetime member of the Indian Natural Fiber Society and a regular reviewer of different peer-reviewed international journals. His specialization is in eco-friendly green chemical processing of textile, nanotechnology in functional material, textile and polymer. And he is going to present his paper on piezoelectric fiber. So, Professor Sir, have I pronounced it correctly? Piezoelectric fiber, a smarter option for energy. So I am very highly interested to know what is there, because this is the first time I am hearing, I am coming into this words piezoelectric fiber. So let's hear from Professor Wazid Ali. Stage is yours, sir.
Yeah. Yeah. So my screen is visible.
Yes, absolutely.
All right. Yeah. Many thanks, Mr. Chakraborty, for your nice introduction, and nice to meet you over here. So as you mentioned, I have taken a topic which is piezoelectric fiber. Rather, it can be piezo also, but generally I call it is piezoelectric fiber, a smarter option for energy. And especially I'll be talking about textile for energy, right? So nowadays energy is really, this is the global trends. People are working on energy, and textile can also take part in that mega trends. And the fiber can also be used as energy storage as well as energy harvesting. So mainly in this presentation, I'll be talking about energy harvesting from fiber structure. So let us look at textile. If you want to define textile, basically conventional definition is nothing but people talk about the garments and different kind of home textiles, or mostly the technical textile nowadays in the hot topic, right? But textile, if you ask me to define textile, so I'll define as a materials, right? So for example, textile, ceramic is a material, metal is material, and polymer is also material, but textile always a polymeric material, but it has different aspects with high orientation, longitudinal orientation, high aspect ratio that provides unique characteristics to textile structure. And rather we call it a fibrous materials, right? So as I mentioned, energy, environment, for example, climate change and sustainable developments are the global mega trends in research and product development. So can the textile technologists can also orient themselves in that mega trends of the research in the current scenario? Yes, it can. So in this presentation, as I mentioned, I'll be talking about energy, environment together, and of course it is sustainable as well. So altogether, energy, environment, and sustainable approach will come forward if we talk about materials which can provide energy, and this is renewable energy, right? So material itself will provide energy. There is no need of fossil fuel and other kind of stuff. So if you look back, the renewable energy source, there are many, right? For example, solar cells are quite famous nowadays and popular, and many installation is going on in India as well. And wind energy, hydro, similarly geothermal and biomass, right? But if you just take this comparison in renewable energy sources, for example, wind, solar, geothermal, hydropower, coal, oil and gas, and lastly, the piezoelectric energy harvesting, which is comparatively a new material, new technology rather, in case of energy harvesting. So if you look at this table, I have taken this particular table from Innovatech, the one Israel company. They are installing these piezoelectric materials in different areas, application areas. I'll be talking about one or two few examples of that. So if you look at these piezoelectric things, everything is good as compared to all other energy source. But the main problem is basically is the maturity of the technology. So maturity of the technology is not enough at the moment, means this is basically the white space for the researcher to work on to mature this technology to beat all other conventional energy sources. as I mentioned, this piezoelectricity is a Greek word. Piezo is a Greek word, and generally it denotes to pressure electricity, right? So by application of pressure or movement in the structure, we can generate some, energy, electrical energy, and it inherently comes from the material itself. And this terminology is not very new. It's a very old terminology. 1880, Curie brothers, they first coined this particular terminology, and this terminology generally, came forward from the material like crystals, the quartz and single crystals. I think regularly we're using some of the stuffs which where actually use piezoelectric materials. For example, gas lighter. So gas lighter, there is ceramic based piezoelectric elements. When we press that piezoelectric elements, it generally creates some electrical charge, and that generally helps to ignite this particular ignition. Generally is going to happen. And similar technology generally used in automotives, different fuel engines and all, right? But piezoelectricity generally, this kind of small application, as I mentioned, is a many hundred years old. But the concept of energy harvesting from piezoelectric materials is basically the people are doing research in the last 1 decades, and mostly on the ceramic and the crystal based material, which is basically uniquely proven and the old concept. But the piezoelectricity polymeric structure, and rather the textile fiber structure, is completely new concept, and people have started doing this in the last few years rather. So if you want to define piezoelectricity, so piezoelectricity basically, as I mentioned, is a material property. When a material, if we provide some kind of mechanical impulse or stimuli, for example, any kind of deformation or stretching or compression, then the material will provide some electrical charge. So that is called direct piezoelectric effect. And on the other hand, if we apply some electric field in that particular same material, which is piezoelectric material, the material will mechanically deformed. So that is called converse or indirect piezoelectric effect. So if you talk about direct piezoelectric effect, means that particular principle we can use as a sensor, for example, pressure sensor, and at the same time that material can also be used as energy harvester. So as piezoelectric material as a sensor has been used for many years, but energy harvesting, as I mentioned, is a comparatively new concept. And actuator means, for example, there are many applications of piezoelectric materials as in actuators. For example, camera, the moment we are taking snaps, so the moment we are putting some, button and also the actuation of the lens and, monitoring, focusing, that is happening through actuation, right? So those kind of actuator application is already there of the piezoelectric material. But of course, those are ceramics and, single crystal, as I mentioned. So mostly I'll be talking about a direct piezoelectric effect for, polymeric or textile structure, which is nothing but application of force will promote to generation of some kind of electrical pulses. There are many examples. What is the motivation for textile technologies to take this technology forward? Because if we look back, though, as I mentioned, last 1 decade, people have started doing research using different kind of crystals or ceramic materials rather, right? Putting up on the floor mat, or even the highway. You can see one club in London, that is in King's Road. They have put all these, dance floor made of piezoelectric crystals or ceramics. And the moment they're dancing means they're actually some kind of deformation is happening in the crystal structure, and that is creating electrical charge, the signal that can be harvested, and that is 60% of the lighting of this dance club. They are producing by dancing itself, means, it's a completely renewable things, means your wastage mechanical energy is going to convert through material structure in terms of electrical energy, right? Even if you think about the gym and other workplaces, and this kind of material can also be installed in the office chairs, floor mat, in airport terminals, railway stations, everywhere. So people are really working on that in different countries to take this particular advantage to power systems, to the street light maybe, or maybe the, some other kind of, powering electronic goods or gadgets and all. Why not textile people will take this concept forward and install in a fiber structure, for example, and can be used as wearables, right? Because every day we're using different kind of gadgets, the heart monitoring, of course, heart monitoring, and maybe there are many applications in sensing. If you talk about remote monitoring of the patients, and for example, the defense people are going out for for months and months in the hilly area, right? There is no electricity, for example, and there are many areas there is no electricity, right? So you need to charge your navigation system, your mobile phones, your other electronic gadgets, but that time you need to carry a big battery in the backpack, right? So that is not very simple thing to carry. So if you have some textile material itself, a kind of energy harvesting structure during your movement, during your walking, during your, maybe you're putting that textile structure within the shoes, so you can produce some energy, and that energy can be stored, and that energy can be used directly to charge your mobile phones or other navigation systems, right? Or different kind of other wearables rather. So wearables is of course is a new terminology, and people are, globally people are working, in this hot topic, right? So if we talk about up to now, just we mentioned that the whatever people are doing in the commercial level, all are ceramic, that is hard material, or the single crystals, that is also hard material. So that is all of course not going to be suitable for textile structure, right? So you need to think about polymeric material, which can be converted into piezoelectric structures. So flexibility is very important, and the application of textile, as I mentioned, is a wide range of applications, starting from the fashion, the self-powered fashion light, and to the defense and medical sectors, and everywhere you can find some huge amount of applications. So if you categorize this material, as I mentioned, ceramic, single crystals, and polymers, and another category people have created, that is the composites, because composites, that unique property, the combination of different materials, polymer as well as other ceramic and single crystals can be mixed together to have enhanced property. So let us look back. What is the requirement of the materials? Means all materials are not piezoelectric, right? For example, whatever material we talk about for textile structure is not piezoelectric, for example, or maybe have very the piezoelectric constant value or the energy harvesting efficiency is very less, which cannot be utilized in different applications. So if you talk about polyceramic material, so it's the fundamental, if you just want to know. So this is nothing but the ceramic, which generally nothing but the metal oxide, right? Ceramic is nothing but the metal oxide, and metal oxide has different kind of metal and oxygen, and means there is a dipole. Metal is positively charged and oxygen is slightly negatively. So there is ionic dipole. It's called ionic dipole. So ionic dipole is arranged in a particular fashion in the crystals of a material. And if it is uniformly, for example, it's a symmetric structure or symmetric arrangement of these ionic dipoles, then there will be no charge generation, right? But if somehow we manage that ionic charge, there is a displacement, there is some kind of asymmetricity in the structure. For example, there is a separation of the plus and minus ion, or minus charge and plus charge in the structure, and that ion separation can be freeze within the structure by application of high voltage. So this is basically the fundamentally how you can prepare piezoelectric materials. For example, we have ceramic, as I mentioned, is the metal oxide, and it has ionic dipoles. So initially the ionic dipoles are randomly oriented in the crystal structure, right? So what you need to do, we need to apply high, direct voltage, DC voltage and all. So what will happen by application of the high voltage, all these ionic dipole will be oriented in a particular fashion, right? So one side will be the positive and other side will be the negative, right? And this arrangement you have to do by application of some electric charge, as I mentioned, allowing some temperature, high temperature, depends on the materials, so that the ions can get some kind of movement, some kind of mobility in the structures to get oriented in a particular fashion. And this oriented structure has to be frozen. The dipole orientation has to be frozen, and that can be done by application of the high voltage along with high temperature, as I mentioned. And during freezing, you need to keep on applying high voltage, but at the same time, you need to take the temperature down. The moment the temperature is coming down to the room temperature, so that this ionic dipole orientation is going to be frozen in the structure. So now the material is ready for application because the dipole is oriented now. Now, for example, if you are taking this material and applying some force or some kind of contraction or expansion, then what will happen? There will be change in the charge distribution. This orientation of this charge is going to be disturbed within the structure, and there will be charge separation, plus minus separation. So charge plus minus separation is nothing but that can be harvested in terms of coulombs, and that is going to be collected as a terms of voltage, right? So similarly, this kind of arrangement can also be done in polymeric structure. For example, I have taken one polymer over here, which is called PVDA, polyvinyl divinyl fluoride, that is actually CS2CF2. And if you talk about CF, that is the also a kind of polar bond. Carbon is positively charged and fluorine is negatively charged. So instead of ionic dipole, we can call it is a molecular dipole, right? So molecular dipole, which is present in the polymeric structure, can be used to have this kind of arrangement by application of the high voltage and freezing the dipole within the material structure. And later on, this material can also be used for energy harvesting. So PVDF is also one of the good material. And generally, if you see, PVDF generally exists in random form. That means this fluorine is randomly oriented, with the true side of the carbon. If you see, there is a fluorine. So if you talk about this dipole, for example, carbon is positive and fluorine is negative. So there is a one type of dipole orientation this side, and another is CF bond in the other side, right? So dipole is going to cancel each other, right? So plus minus and plus minus is going to cancel each other, means net dipole moment in this particular polymeric structure is rather zero or is negligible. So that is actually nothing but the crystal structure, which is called alpha crystal. So alpha crystal of PVDF is not ready for providing piezoelectric property. But if somehow we can manage this, fluorine is oriented in the other side, instead of this side, if you take this fluorine in the other side, for example, fluorine is present in the same side of the carbon atom, then what will happen? In one side will be carbon and another side will be fluorine, right? So all the fluorine atom will be one side of the carbon, and all the hydrogen will be the other side. So carbon fluorine, there will be some net dipole moment, or that is called molecular dipole, which is later on going to be oriented in a particular fashion by application of the high voltage. And that particular oriented dipole crystal structure is called beta structure. So alpha versus beta structure of the polymer is very important. And this can happen in other polymer also, but I have taken this polymer because the carbon fluorine is, the dipole moment is very high, right? Because fluorine is highest negative in the series, if you see. So alpha is non-piezoelectric, as I mentioned, because it's the random orientation and fluorine is the both sides. So dipole moment is going to cancel each other, but beta structure is basically which is desirable for piezoelectric property. And beta structure is generally is actually the structure of interest, but that can be obtained in different process. For example, high voltage application, as I mentioned, or maybe you can have stretching operation after formation of the fiber or film. So that stretching can also convert alpha to beta. So that kind of arrangement you need to do in the crystal structure before the material is getting ready for piezoelectric application, right? So ceramic and polymer, if you talk about, but ceramic has highest piezoelectric property because the dielectric constant or dipole is very high, as I mentioned, because the dielectric constant is very high in the range of 1700 to even more than 3000, right? But all other characteristics is good in ceramic material, but the ceramic is not flexible, of course, so it cannot be used in textile, or maybe in polymer structure we cannot make it in different shape, or maybe wearables and all. But polymeric structure, on the other hand, although PVDF has some kind of property, but it cannot compete, right, with the ceramic material because the dielectric constant is very less, 8 to 12 kind of range, right? But although it is highest among all other kind of available polymeric structure. But the main advantage of polymeric material is the flexibility. So this is basically true for all polymeric structure. Polymer structure is very flexible, stretchable, but it lacks functional property everywhere, right? So that is the things we need to talk about. So the option is, can you combine together? For example, if you take polymer and take ceramic structure, which I mentioned in the composites, right? So composites can be one approach where the flexibility of the material can be maintained, and that composites can be in terms of film as well as in fiber form. So we need to think about what kind of form we're talking about and what kind of process we're talking about, right? So the ceramic material, or the single crystal rather, which can be converted into different nano shapes, right? It can be nanoparticles and nanorods, right? So those nanoparticles, which is highly piezoelectric in nature because it's inherent ionic structure, ionic dipole, and which can be incorporated in the PVD, like material like PVDF. PVDF also to some extent has piezoelectric property and can further be enhanced, by along with this composite approach, right? So as I mentioned, preparation of piezoelectric material also needs high voltage application, right? High voltage application. But in normal spinning process or film formation, we don't use any kind of, electrical voltage. So what you need to do after formation of these, composites into in the form of filament, or maybe in the form of fiber, or maybe in the form of film, you need to go for separate pooling operation. That is called pooling operation, means high voltage operation, so that the dipole is going to be oriented in the structure along with some temperature. But if we talk about electrospinning, that is a unique technique. So just I wanted to talk about this process because electrospinning is nothing but the application of the high voltage. And this high voltage, we can use polymeric solution along with filler together, and we can, spin out this fiber, nanocomposite fiber, in terms of, nanostructure rather, where in situ pooling can happen, because this material, the polymer as well as filler, is going through high voltage during preparation of the fiber itself, right? So if you get this particular, nanofibrous wave in terms of non-event structure, for example, and that is already pulled in the spinning operation itself, right? So there is no separate pulling operation or high voltage application is required. So that is the uniqueness of this particular, techniques. But it's not like that only this is the only technique for preparation of the fiber or textile structure. Rather, we can have filament, normal melt spinning, or solution spinning. So later on, you need to go for additional step, which is called pulling operation. So in our research, actually, we have taken one ceramic material, which is nothing but sodium potassium niobate, which is excellent in piezoelectric, characteristics. There are many materials, of course, lead-based materials. For example, PZT is very famous in terms of piezoelectric property, but this material is going to, is going to ban in this, already banned in the European markets, and even in India, maybe is going to phase out because of the lead content, which is very, toxic in nature. So people are looking for some lead-free material, of course, and we have synthesized a new material, new structure, which is sodium potassium niobate, and we synthesize in terms of rods, right? So rods, why actually rods? For example, if we talk about particles, so if you want to take uniform properties throughout the fiber structure, then particle has to be stayed everywhere, right? Everywhere the particles should be seated. And if you load more and more particle in the textile structure, the fiber structure is going to be brittle and brittle, right? So we thought that can we synthesize this filler material also in the terms of, some aspect ratio, so it can be flexible as well as a continuous deposition in the fiber structure, and we can at the same time at lower loading as compared to particles, we can maintain the flexibility of the structure as well as we can have enhanced property, right? So this is actually, we have carried out different kind of characterizations to prove that this structure is firm or not. And its crystal structure is very important for piezoelectricity, as I mentioned. For example, for PVDF, as I mentioned, it should not be alpha, it should be beta. And similarly for ceramic also, it should be orthorhombic, or it should be hexagonal. It should not be like cubic structure. Cubic structure means is basically the symmetric structure, means the dipole moment are balanced. The dipole total resultant dipole moment will be less, or maybe it's towards zero. So crystal structure of the filler is also important, which actually we have maintained over here. And then we have incorporated into this filler into PVDF, and in terms of, first of all, we have, we have proved this concept in the terms of composite film, and this film is characterized for different kind of structural features. For example, as I mentioned, if we pure PVDF, if you characterize this pure PVDF film, then we are getting some beta concentration, for example, 65% beta crystal phase and all, which is desirable. But the moment we are adding this, filler structure, for example, 5% KN, 10% and all, so beta percentage of the PVDF is also going to increase, because metal oxide has different kind of, hydroxyl group on the structure surface. So it will have some kind of interaction with the fluorine group of the PVDF, and that will essentially actually helping to formation of the more beta phase in the PVDF structure, right? So that kind of concept has been proven over here. The arrangement of the filler within the structure to have more beta part from the polymer part as well. And the major challenge is the inorganic organic, mixing, right? Inorganic organic mixing is a major challenge. So what we have done, we have modified the filler, that is the piezoelectric filler has been modified with some coupling agent, which is basically organic in nature. So it will have, more miscibility with the PVDF polymeric material and all, right? So agglomeration is less during spinning or film formation. And at the same time, dispersion is proper, better along with the surface modifier, right? So that concept is also been proven over here. Uh, and ultimately, we have seen that if we talk about this is the nanocomposite, film rather, and we have characterized then in the voltage, generally we got in the range of 5 to 6 volt. This is in the film form. But if you talk about the electrospinning, as I mentioned, we have taken the same combination, that ceramic and PVDF together, and went through the electrospinning process where we are applying high voltage, of course, and in situ pulling, as I mentioned, in situ pulling is happening over here, and that is the main advantage of using electrospinning for production of this kind of device. So and also mechanical stretching is also happening, right? In this case, the stretching is happening on the polymeric part. So more and more stretching means more and more beta alpha is going to convert it into beta from the PVD part. And same time, the dipole is going to be oriented by application of the high voltage. So in this electrospan fiber structure, we got 17 volt output voltage, right? 17 volt output voltage as compared to the film. Film actually, as I mentioned, 5 to 6 volts. But if you talk about this nanofiber structure, we got 17 volt output voltage. Similarly, we have surface modified, as I mentioned, KNN also has been incorporated in the electrospan fiber. And because of the surface modification, more proper distribution, more interaction with the polymeric chain of PVDF, more formation of the beta structure of the PVDF, and even there is an improvement in the voltage generation, the level of 21. Average voltage I'm reporting, that is 21 volts. And another concept has also been, conceptualized over here. For example, if there is a charge which is going to produce in the structure, so that charge has to flow, right? Flow on the surface, so that by application of some electrode on the top and bottom, we can harvest the charge. So if we include some kind of semiconducting material or maybe some kind of conducting material within the fiber structure, along with PVDF, KNN, and for example, CNT, we have used as conducting filler, and also zinc oxide and a semiconducting filler. And by the way, zinc oxide is also piezoelectric in nature. And because zinc oxide is semiconducting as well as piezoelectric in nature, the output voltage is further higher, 25 volts. So if you incorporate this kind of semiconducting filler or maybe conducting filler in the structure, so we can expect higher output voltage, because it will facilitate the movement of the charge within the structure towards the electrode, top and bottom electrode of the material. So if you compare this different, process, for example, film, then surface modified filler along with, PVDF, then electrospan, then surface modified electrospan, then even combination of PVDF, KNN, zinc oxide, PVDF, KNN, and CNT. So there is some variation, right? So we have optimized the different kind of combination, different kind of process and all, and of course, melt spinning as well. So melt spinning along with KNN and PVDF is getting only 3 to 4 volt kind of stuff. Of course, this particular material is not pulled, but obviously if we apply high voltage over here after filament formation, then definitely this voltage is going to improve, right? So at the moment, in situ pulling, we are taking help in the electrospinning process, and we can see that we can harvest up to 25 volt voltage from the structure, from the material itself, that nothing is there on the material. So we are not dependent on the sun, we are not dependent on the wind. For example, wind energy or sun energy means you are absolutely dependent on there is sun, then there is energy. If there is a wind, then there is energy. But this is basically the material property. And if the material is designed in such fashion, then if we wear this textile structure in the fibrous structure, rather in terms of in piezoelectric materials, then it can provide some energy which can be used, right? These are some comparisons, whatever we have done in the research work as compared to other reported research work along with barium titanate and all, and KNN, of course, electrospan. But our approach, 3% loading, which is basically the nanorods. Nanorods, as I mentioned, is giving highest property as compared to particles, and we could harvest 17 up to 17.5 volt, only 3% loading in the electrospan fiber. The loading is very, very less as compared to the other reported value. So this is a small video. For example, we have how this LED can be sorry. So with our material, we could, flash out some LEDs also, multiple LEDs. We have tried to write IITD over here, but it is not properly visible, but absolutely from the structure. So it's not, there is nothing, only the material is providing this kind of voltage, which is helping to provide this charge, right? So along this, we have published many papers in this particular topic. As I mentioned, this is what I presented is ACRB funded project, and this entire work was done by my PhD students. He is already got PhD degree from Satyaranjan Bairagi, and one of my MTech students, Miss Swagata Banerjee, right? So I just want to acknowledge them because I'm presenting their work. So characters and facilities over here in NRF and Nano Research Facility and Central Research Facility at IIT Delhi. And of course, the fund we have received from DST, Science and Engineering Research Board. So this concept for the textile is very infancy stage, rather, I would say. So started research in a few years. So there is many things to do to optimize the structure in the different combinations in the fiber and filament form, and their integration in woven structure or knitted structure or maybe non-wovens. So that is the area of research in the next few, I think, years, I would say, is going to be focused on that. So there is a hope for this particular topic to work on and to find some, of course, some possible strategic application and all. And thank you so much for your attention.
Yeah. Thank you, Professor. It was very interesting topic. And now we all know what is this piezoelectric, uh, piezoelectric, sorry. And it's a great effort, I think, for these renewable energy sources, as you have correctly said, that these are the global trends, and also fascinating to see how you have come across different challenges. First of all, it was means there are challenges of whether textile material has this capability, it has flexibility, but lower piezoelectric, and so you are mixed with ceramic, then you solved it in some other ways, some surface modification. So many challenges, and gradually you have come, you have done all the modifications. That's, I think, showing a great potential for the future. Wish you all the best. And I don't see till now any question, so requesting all the audience to write their questions in the chat box. And okay, already we are late, so let's go quickly to the next presentation, that is by Ankur Shukla. He is from Department of Textile and Fiber Engineering, IIT Delhi, and he is going to present study of volumetric behavior of various dopants and electrochemical polymerization for preparation of electroconductive polyester fabric. Ankur, my request to you is that if your presentation can be in less time. Wish you all the best, Ankur. Stage is yours. Thank you.
Thank you, sir. I'll try to complete it soon. And good afternoon, everyone. So, myself, Ankur Shukla, and I'll be sharing my presentation on studies of voltammetric behavior of different dopants and electrochemical polymerization of pyrrole for preparation of electroconducting polyester fabric. So there are different methods by which conducting fabric can be prepared, such as chemical polymerization, chemical vapor deposition, photo-initiated polymerization, plasma-enhanced polymerization, and electrochemical polymerization. Out of these, the electrochemical polymerization is one of the best methods since it provides much better control over the process parameters and to tailor the properties of the resulting polymer. So this includes an electrochemical cell, such as shown here, and it includes a monomer. In our case, it is pyrrole. And then we have used different kind of dopants to increase and to change the conductivity of the polymer formed. This includes PTSA, petolene sulfonic acid, anthracnone sulfonic acid salts, sodium nitrate, and oxalic acid. So to see the properties of these, we have used cyclic voltammetry. So it was done in two ways: potentiostatic voltammetry, where the applied potential is varied and the system current is being observed, and the other one is the galvanostatic voltammetry, where current is varied and the potential is being observed. So in both cases, it was observed in the 5 cycles that these compounds which are being used for the polymerization, they get ionized after some time. So after the ionization, these get embedded into the polymer film and then provide the desired conductivity. So the method which was used for polymerization is also known as chronoamperometry, where a constant potential is being applied for the desired time. So we have done the process for 30 minutes, which is around 1800 seconds. And it was observed that on when the potential was applied with the monomer, this is the right figure, and without the monomer, which is pyrrole, this left figure. So the behavior of the current was almost similar. And in all the case, all the dopants, the behavior of this current was similar. After a slight increase initially, it becomes almost constant line. But in case of only this one compound, AQSANA, the current in the system is very less. This was found due to the lower solubility of this particular compound, which limits the current uh, through the electrochemical polymerization cell. So to counter this, the lower concentrations of the solutions were used, and then again the properties were compared, and it was observed that this weight add-on percentage increases every time as we increase the polymerization voltage. So in case of all the dopants, this current is increasing, and this weight add-on is increasing, and the polymer formed is higher, but except in the case of oxalic acid. In other figure, chronopotentiometry, when constant current was applied for polymer formation, again the weight goes on increasing, but after certain current density, these chemicals start ionizing and they decompose and do not participate in the reaction further. So being more stable system, this chronoamperometry process was used and constant voltage was applied. So in case of oxalic acid, it was found that the oxidation potential of oxalic acid is 1.01, which is very close to the oxidation potential of our monomer, around 0.7 volts. So as the polymer is formed, this oxalic acid starts decomposing and forms carbon dioxide and then leaves the system. So it kind of is not a good dopant for our work. So again, the charge flow through the system was measured, and it was observed that as the voltage applied was increasing, this charge flow goes on increasing. But in case of sodium nitrate, it is almost uh, correspondingly increasing, such that at 1 volt the charge flow is less in sodium nitrate. Then at 3 volt it is increasing, and at 5 volts it is highest. But we can see that in case of AQSA and PTSA, this charge flow decreases as the voltage is higher. This was again due to the same reasons that these compounds get decomposed, and therefore the concentration decreases within the solution, and therefore the charge flow is less. Similarly, the current behavior was observed during the formation of polypyrrole polymer. At 1 volt, the current was lower in all the cases. At 3 volts, it was higher, and at 5 volt, it was again highest. So we can see the behavior of sodium nitrate, this red colored line, is again similar. It is increasing with the voltage. And in case of AQSA and PTSA, it is again decreasing at 5 volts. So we have used conditions of 3 volt, for polymerization voltage, and except the oxalic acid, we have used and compared these three compounds for doping behavior. For confirmation of doping that these compounds are present within the polymer, this EDX analysis was done, and sulfur contents were observed in case of PTSA and AQSA, and the higher percentage of nitrogen and traces of sodium confirmed the presence of sodium nitrate. In case of oxalic acid, the only confirmation was higher carbon content, since it leaves the system and becomes carbon dioxide. Further confirmation using FTIR was done, and the stretching peaks at 1410 confirmed the presence of sulfonic groups, and 1301 and 883 peaks confirmed the presence of nitrate ions, and few traces of at 1190 peak confirmed the presence of oxalic acids, that is carboxylic acid formation. Then XRD behavior was studied, and it was observed that in case of AQSA-Na, the crystallinity is very high compared to all the other compounds, since the peak is very narrow and sharp. So we can see that the conductivity also would be higher when AQSA-Na is being used. So since the sodium nitrate was allowing higher current to pass through the system, it was combined with different dopants, like PTSA and AQSA are known to be good dopants. So it was combined, and combinations were sodium nitrate PTSA, sodium nitrate AQSA, and PTSA plus AQSA. So in this case, it was observed that highest current was there when sodium nitrate was combined with PTSA in the electrochemical system. So this higher current, this current is not just the algebraic sum, it is higher than the summation of these two currents. These are the individual currents due to the individual compounds, and this is the current obtained when the polymerization was done using this sodium nitrate PTSA combination. So higher is the current, then higher is the energy available for polymerization, and which this leads to higher polymer deposition, which certainly results in higher conductivity of the polymer formed. So this graph this confirms that the sodium nitrate PTSA combination is the best one, since the resistance is lowest with this combination. So next was the image analysis was done, and polymerization was performed over a stainless steel electrode, and surface coverage was checked using this image analysis, and we can see that in case of sodium nitrate PTSA combination, the almost 97% of the area of the electrode was fully covered, and about 3% area was uncovered, and like polymer did not deposit on this much area. So this is again beneficial, because in case of textiles, we need full area coverage, and so that the polymer completely encloses the fibers and the yarns for higher conductivity. Again, in case of sodium nitrate AQSA, this coverage ratio was good, but it was not like compared to the sodium nitrate, it was not good. Then again, AQSA and PTSA were used for polymerization, and we can see that around 21% area is uncovered from the polymer, which means it cannot be used much efficiently for polymerization. So further, this study was taken for over the fabrics, polyester fabric, and in first step, this normal polyester fabric was converted to slightly conducting polyester fabric using vapor deposition method, and then further, since we cannot use normal non-conductive insulating fabric in as anode or cathode in the electrochemical polymerization, we have to do this step. After this, the fabric was used as anode and placed into the electrochemical cell, and the combination used was sodium nitrate PTSA at 3 volts of polymerization voltage. Then electrochemical polymerization was carried out for 30 minutes And we can see this black colored polymer deposition. And we can see that about 10% of the fabric weight, the polymer has been deposited, and the resistance is about 2.52 kilo ohms, which can be further tailored and reduced as per the requirements of the application. So we concluded that this ionization behavior of the dopants largely affects the resistance of polypyrrole in electrochemical polymerization. The combinations of dopants could be used for imparting different properties to polypyrrole. Using a good dopant with a good charge carrying entity, in our case it was sodium nitrate, results in higher polypyrrole deposition and thereby lower resistance of the polymer. Then the system current, which was observed in case of combination of dopants, was higher and more than the algebraic sum of the currents observed due to the individual dopants, which is good for polymerization. Then lastly, the applications like the fabric could be used not only for anti-static applications, but we are also trying to develop some flexible sensors based on this polypyrrole coated fabric. Thank you.
Thanks, Ankur, for this beautiful presentation. I think if it would be used in this anti-static and other activities as well, it would be a great benefit for all of us. And
Yes.
our next speaker is Prantika KP. So she is talking about molecular characterization of Hibiscus rosa syngenesis and its antimicrobial activities on textiles. So welcome Prantika, and request you if you can keep your presentation a short one. Thank you. Stage
Sorry
is
to interrupt,
yours.
sir. Prantika is not available. We can go with the next speaker.
Oh, I see. Okay, then the next speaker is Kalai Selvi, and she will be presenting a paper on study on moisture management characteristics of tri-layer knitted fabric for sportswear application. Okay, welcome Kalai.
Kalai Sylvie, if you are present, please.
Hello, ma'am. Can you hear me?
Yeah, we
Yeah.
can.
Okay, ma'am. I'm looking how to share this, share my screen.
There would be a green arrow on the bottom. Just
Okay.
click on that share screen.
Okay, ma'am.
And Kalai Selvi, please can you put your video on the on mode? We can't see you.
Okay, ma'am. 1 minute, ma'am.
Just you need to click on that green icon, then you will be able to share your screen.
Even if I click it, no, I couldn't share my screen.
Once retry, because that is only the option. Just click on that share screen. There would be share screen option.
Share.
The third one from the bottom corner.
Sorry, I can't share it. Oh my god, it is not sharing.
No. While
Is
you
there any
click,
other person to present?
No, you're the last one.
You should join from a laptop, not from mobile.
Oh, okay, sir.
Okay, then let Kalai Selvi try to present the paper. Meanwhile, if you have any question, please put your video on and then ask the question to all to the speakers. First, you name the speaker to whom you want to question, and then you can ask your question. Okay, so I think till now nobody has asked. So, Professor Apurbo Das, I have a question. In your presentation, that filter you were making, so is it now tried and implemented anywhere?
No, it has not been implemented yet, but we are in a we are trying to do it actually, because it requires government's intervention. Okay, you have to go through government. You cannot do directly. Okay, that's
okay.
It's basically you have to go through the different level, state level. You have to go through the block level, then panchayat level, like that. So that is it's not that straightforward. And as it is a drinkable thing, that we need approval. It's our we have tested our thing, because as it's consuming, people are, so we need some actually approval from our the agency, that food and all these agencies. Okay, that is also.
Right, sir. Right. And what about the frequency of the changes of the cartridges?
Cartridge is very less. Basically, it takes a long time after, because the main problem is the turbidity problem. Depending on the turbidity of water, that is the issue. But otherwise, the nano thing and all this, it's a long term, because you are getting the second stage filter only maybe 0.1 parts, 0.2 3% turbidity is coming. So the very less particles are coming, because but that if you have a very dirty water, then it may block, and that too you can actually wash out. It's not, you can reuse that normally, but after a certain time it's there. And it has got great potential, because it's a no power, no electricity, no mechanization, nothing is there. Basically, that's the thing.
Yeah, absolutely, absolutely. And another question, sir. In this means nano, I can understand it's the silver particle, nano silver particle, which is doing the antimicrobial activities. Now, is there any life of that? Means one part is you have explained that the life of the cartridge filter is higher as delta P, that is pressure difference are not great. And but what about the microbial killing efficacy life of the filter?
Killing efficacy life, that also, that long term thing we have not used. Basically, we have not, because it just student has completed his PhD and all this, and project is completed. But these are the issues we have to address basically gradually. What is the in long term? How is the efficiency will be there? And because anyway, there is nothing. It's basically it's a silver nanoparticle will be there. Depending on the leaching potential, leaching quantity, that may reduce little bit. Otherwise, if it stays, and we have observed that leaching is it's very less, very less, as far as much lesser than the WTO guidelines, the silver content. So that way the life which will be long life, but it's true that we have not actually evaluated that part.
Okay, great. I think now is Miss Kalai is ready to share the presentation. Vipula?
So she's present. Yeah. Kalai, please can you share the just presentation mode? Yeah.
Is it visible, ma'am?
Yeah, your slides are visible.
Okay. Am I audible?
Yeah, you're completely audible, but your video is off. Can you put your video on?
Okay, 1 minute. Yes, ma'am.
Yeah, it's completely visible.
Okay, ma'am. Thank you. Good afternoon, everybody.
Video is
Myself.
not on.
It's not on, sir.
Yeah. You are not. Yeah.
Okay, sir. 1 minute. Okay. Good afternoon, everybody. Myself is Kalai
Sorry to
Chelvi.
interrupt, Kalai. We can't see your presentations.
I think.
Yeah, I guess one of the thing would be on at one time. Your
I don't know
journal
how to.
background.
What
Okay,
should I know now?
no problem. No problem. Carry on with the presentation mode.
Thank you, sir. Thank you. Today's topic for the presentation is a study on moisture management characteristics of tri-layer knitted fabrics for sportswear application. Introduction. Nowadays, clothing functions as a resistance to heat and moisture transfer between the skin and environment. The control movement of water vapor and liquid, that is the perspiration from the surface of the skin to atmosphere through the fabric, is defined as a moisture management. The efficiency of the active sportswear increases when two or more parameters are combined together and made out of a fabric. Multi-layer fabric is generally showing a betterment in all the properties that is needed for an active sportswear application. Nathan et al. They carried out their research in bilayer fabrics, making use of a combination of fibers possessing wicking and hydrophilic properties to improve moisture handle and aesthetic performance of the fabrics. This research came out with the finding that moisture vapor transmission and absorption both are good in bilayer fabric. The bilayer fabric made out of polypropylene and viscose is said to possess a better wicking behavior, drop absorbency, and stretchability property. And air permeability is found to be good in polyester viscose combination, and the thermal property is in polypropylene cotton combination. As an outcome of his research, the bilayer knitted fabric made out of polypropylene and viscose is said to possess all the characteristics that is suiting for an active sportswear application. The thermal characteristics of single and double layer fabrics were studied by Gupta et al. In their study, the fabrics were layered with and without air gap between them, and the effect of a multi-layer garment was evaluated. When the inner and outer layers of the fabric are linked together, the thermal insulation rises, making the fabric more comfortable to wear. Geeta Margaret and Kavita, they developed a bilayer fabric of modal and polyester yarn, and it is found that plaited jacquard fabric is better when compared to that of interlock jacquard structure, making it more suitable for sportswear with good moisture absorbency, thermal resistance, and wicking property. This is because the plaited jacquard fabric has a good absorbency and good drying in nature. Kandavadivu carried
Acha,
out their...
excuse me, Kalai. Can you go
Yes.
to your studies first?
Okay, sir.
But that would be better.
Okay, sir.
Yeah.
This is my study. These are the materials and methods I have taken up for my study. Three tri-layer knitter fabrics were developed on a Pauling double knit interlock knitting machine, that is PLKD 2.5D, Taiwan, with 36 feeders, 28 gauges, and 84 feeders. Three samples of tri-layer knitted structured fabrics were developed. That is the inner layer, which is the skin contact layer, is made up of bamboo. The outer layer, that is the environment exposed layer, is cotton. The middle yarn, I have used various yarns, that is the polyester. The filament is 72, monofilament 20 denier I have taken up, and wool, that is of 60s count. These are the tri-layer knitted samples I have studied. These are the sample codes for bamboo monofilament polyester cotton yarn, that is B, MDPF, and C. For bamboo micro monofilament cotton, B, MF, C, that is bamboo wool cotton, BWC. I have used a moisture management tester for testing all these three samples according to the method AATCC 195 2012. This instrument is used to measure the liquid moisture transport in multiple directions. These are the results after testing for moisture management property. The wetting time is observed in the sample 3. A good wetting time is observed in the sample 3. The sample with the inner layer bamboo, middle layer wool, and outer layer cotton. This means the sweat is slowly absorbed compared to the other fabrics. The top and bottom surface in the sample 1, the sample with the inner layer bamboo, middle layer microdenia filament polyester, and outer layer cotton fabrics have the lower wetting time. If the wetting time is lower, that means good wetting time is observed. The middle layer made from the microdenia filament polyester shows an excellent wicking property that supports the transfer of sweat between the layers of the fabric. In general, the hydrophilic nature means materials with special affinity for water. Those means maximizing contact with the fabric. Microdenia polyester hydrophilic nature is possessed by the cotton fiber having a good surface bonding nature for water molecules. The sample, the three bamboo wool cotton confirms that there is very poor transfer of liquid to the bottom layer of the fabric. These are the results. You could see the wetting time is less for the sample 1 and higher for the sample 3. That means a good wicking moisture property for sample 1 and poor for the sample bamboo wool cotton. Absorption rate. Compared to the absorption rate, you could see the results. The absorption rate for bamboo microdenia filament polyester has good absorption rate for seconds, and for bamboo wool cotton, the absorption rate for the top and bottom surface is comparatively lower than that of the other two samples. The wetting radius. For the wetting radius also, the highest maximum top wetting radius are seen in bamboo microdenia polyester filament and cotton tri-layer knitted fabrics. This is because the capillary forces facilitate the easy transmission of the moisture through the filamental surface of the microdenia polyester filaments. Because of the excellent capillary action of the wetted radius on either side of the fabric are very high. Compared to the other entire tri-layer knitted fabric, sample 1 is observed to possess higher moisture wetting radius when compared to the other fabric samples. The lesser diffusion property of the wool and cotton tri-layer knitted fabrics as compared to the other tri-layer knitted fabric is the main reason for the drop in performance. Means the lesser diffusion properties of the wool. The filaments of the microdenia polyester filament has good capillary nature in comparison to the other developed samples. Only because of that, the maximum wetting radius is found. Spreading speed. Minimum level of air is trapped within the surface of the fabrics because of the finer filamentous nature of microdenia filament polyester. Only because of that, the spreading speed in top and bottom surfaces higher for minutes. And for the sample 3, that is bamboo wool cotton, the spreading speed is comparatively less compared to the other 2 samples. Less drying time is one of the most important physiological parameters for the comfort. The spreading speed values of the cotton layers are lower, and the bamboo microdynia polyester filament cotton has good spreading speed. The sweat is well absorbed by the fibers due to its excellent hydrophilic characteristics of bamboo and microdynia polyester fibers in both sides of the fabric, making it to possess a high spreading speed comparing to the other fabric samples. Then the result for accumulative one-way transport index and overall moisture management capacity. By using a wide variety of yarns for different moisture transport properties are achieved when the sweat can be easily transmitted, giving an excellent dry feel, making the wearer more comfortable. These are the figures 5 and 6. You could see the accumulative one-way transport index for bamboo microdynia filament polyester is very high, and the overall moisture management capacity for the same fabric, that is the bamboo microdynia polyester filament and cotton fabrics, has good OMMC values comparing to the other 2 fabrics. The fabric that touches the skin becomes dry at a faster rate due to the excellent absorption rate and higher maximum wetting radius and spreading speed. So through the results, you could see the bamboo microdynia polyester filament stands first in the result, and followed by the other 2 samples. Conclusion. The moisture management features of produced dry layer knitted fabrics made up of range of fibers in inside, middle and interior outside, middle and interior layers are investigated in the study. The overall moisture management capacity of the bamboo microdynia polyester filament and cotton fabric is determined to be quite good. As the evidenced by OMMC values, the bamboo microdynia polyester filament cotton fabric has a good moisture management transmission property. The MVR and MVT of the fabric influences the spreading area and fabric moisture, having microdynia filamentous polyester yarns as it's in the middle layer. The capillary nature of the yarn is mainly the reason for good moisture management property. So this is exhibited by the sample bamboo microdynia polyester filament and cotton. This tri-layer knitted fabrics are suitable for textiles and fabrics used for sports due to the faster release of the perspiration and sweat from the skin. So giving an excellent dry and comfort feel to the wearer, making them perform well in all of their activities. Thank you. These are the references for the studies. Thank you. Thank you so much.
Yeah, thank you, Kalai, for your presentation, and hope your findings will be valuable for Indian sports, Indian athletes.
Thank you, sir. Thank you.
And now, as we have already heard 4 paper, and now if you have any questions, we have still some time. So if you have any question, we can take it.
Sir, good afternoon. Myself, Pranam Nandi from Guinea Filaments. I have a questions.
Yeah, please.
Actually, Kalai Selvi has considered bamboo fabric as a inner layer and cotton is the outer layer, and the polyester monofilament as a middle layer. So I have a just query that what was the prerequisite that insisted her to consider bamboo as an inner layer rather than cotton? Is there any special logic or something else?
So that is because the evaporation percentage for cotton is absorption rate for the cotton is very less compared to that of the bamboo. So so in considering both the fabrics, the results are higher in bamboo. So I chose bamboo, sir, because the absorption and wicking property for the cotton is comparatively less than that of the bamboo. With the testing
And
results, I have chosen.
And in textile, just like you have used polyester microfilament as a middle layer, which is
Middle layer, yes.
hydrophobic in nature, and you have used both bamboo and cotton, which is hydrophilic in nature. So, is there a special reason to use the hydrophobic filaments in the middle layer? So, it's special any logic, or you have just taken as a trial?
So it's that I wanted to try the middle layer as microfilament polyester because the results in the past studies were good. So I thought of taking their results and wanted to put in my studies and
just as observation, just is continued because we are putting hydrophobic in between to hydrophilic. So that was my query. Okay, thank you.
Okay, thank you, Pranab. Any other question?
Yes, myself Arun Nag from Giti Filaments. Yes, I have very simple question from Ms. Kalai. I would like to know what were the GSMs of these three different layers. Were these equal, or there was some variation between first, second, and third layer in terms of GSM?
Sir, I have taken the counts for very similar, sir. For bamboo and cotton, that is, I have taken 40s count, sir. And I have taken the microdenier polyester filament, that is of 72 filaments. So, and only the wool is of 60s count, sir. So, only that is the GSM was bit higher and not of equal to bamboo and cotton, sir, because the wool was not available for the study, and the bamboo and cotton is similar GSM, sir.
Okay, because GSM itself will play some role for
Yes,
the
sir. Yes, sir.
moisture management and all those.
Yes, sir. The cotton, the count is 40, sir. It is a finer count, and it actually gives a good, better results.
No, yes, it is count 40 means that will be the count of the yarn used for
Yes.
making the fabric. But what
Yes.
was the GSM of the resultant fabric? That matters.
Okay, sir. Okay.
Okay, no issue. Please check.
Thank you, sir.
Thank you, Naksab. Any other question? Okay, I think there is no more questions. So it was a fantastic session. Thanks to all the audience as well as our eminent speakers. Now, may I request everybody to open their video so that we can take a screenshot and store it as a remembrance. So everybody can now open their video.
Excuse me, sir.
Yeah.
Sir, I'm Pranita. Our presentation time is between 12 to 12:10. We couldn't make it on that time. Can I present now?
Oh, Pranita, I think you have missed the bus. But how much time you will take? Can you
Sir,
finish
for
it
10.
in? Can you finish
Sir?
it in 10 minutes?
Yes, sir.
Okay, in that case, I think we can have it because we have time of 15 minutes left. So yes, Pranita, please go ahead with your
Can I?
presentation. And Pranita is basically from I think Banari Aman Institute of Technology, and
Yes,
she
sir.
is talking about molecular characterization of Hibiscus rosa sinensis and its antimicrobial activity on textile. I am especially highly excited to hear about this paper. Yeah,
Shall I
Pranita.
share my screen, sir?
Yes, please.
Pranitha, there would be a green arrow on the bottom which shows the share screen. You can click on that. Pranitha, we can't see your presentation yet. We could see that you have started share screening.
Yes, ma'am.
Yeah, now it's visible. Yeah, no,
Ah.
it's gone.
Yes, ma'am. Yes, ma'am.
Retry by the same process.
Now it's visible, ma'am.
It just shows that you have started the share. Yeah, now we can see it. Just make it to the first slide. Like it's a very blurred version.
Now is it visible, ma'am?
Your slides are visible, but the screen is freezed right now.
I didn't change the slides till now, ma'am. Can I start?
Yeah, we can
okay.
see.
Let's
Your
see.
video is not on.
Okay. I should start my video also, ma'am.
Yeah.
Yes.
Am I now visible?
You're not visible, but I guess there is some network issue at your end.
Now,
Yeah, you're visible now.
okay. Happy afternoon, everyone. I'm Pranitha from Bannaraman Institute of Technology. My topic is about molecular characterization of hibiscus rosa sinensis and its antibacterial activity on textiles. These are the topics covered in my presentation. Introduction. Hibiscus rosa sinensis is a bushy evergreen shrub or small tree growing 2.5 to 5 meter tall and 1.5 to 3 meter wide with glossy leaves and solitary brilliant.
दो पेपर और है मस्किटो ने उसके natural.
Sir, I can't hear you.
No, yeah, please, you continue, Pranita.
Okay. Brilliant red flowers in summer and autumn. The 5 pleated petals are 10 centimeter in diameter with prominent orange tipped red anthers. The root is a branched taproot. Materials. Hibiscus rosa sinensis flowers were collected from the garden in Satyamangalam, Tamil Nadu and dried. Bleached cotton fabrics with the following specifications were used as indicated. We used 100% cotton fabric with 90 GSM, 60 watt count, 50 weft count, 62 EPI and 50 PPI. Potassium alum, which is the hydrated form of potassium aluminum sulfate and has the chemical formula KAlSO4 twice 12H2O. Potassium alum is a fine white powder was used as the moderant. Ethanol has been collected from Department of Biotechnology for required purpose. Ethanol with the chemical formula C2H5OH is volatile, flammable, colorless liquid with a slight characteristics order. Methods. Hibiscus rosa sinensis flowers were collected and washed for a couple of minutes. Subsequent to washing process, the unwanted dirt were removed and just fresh flowers were taken for next process. Flowers were spreaded in one plate and dried in shade. After about a week of drying, the dried flowers were collected from the plate. The powdered plant material was extracted with ethanol by adding 150 grams of hibiscus rosa sinensis in 250 ml of ethanol. The ethanolic extract of hibiscus rosa sinensis was prepared with Soxhlet apparatus. Hibiscus rosa sinensis is powder of 250 gram was packed in Wattman filter paper and placed inside the thimble which was loaded into the main chamber of Soxhlet extractor. Distillation flask was filled with 250 ml of ethanol and was placed in the heating mantle. The Soxhlet extractor was placed on the top of it. the flask. The various concentrations of the extract were obtained, that is at 25%, 50%, 75%, and 100%. The ethanol evaporated from the extract at 78 degrees Celsius using distillation process for 30 minutes. The ethanol-free filtrate was used for further application and analysis. Bacterial strains. The antibacterial activity of cotton fabrics treated with hibiscus rosa sinensis extract was evaluated with Escherichia coli, a gram-negative bacterium, and Listeria monocytogenes, a gram-positive bacterium. These two organisms are used for antibacterial susceptibility testing as reference strains in according to AATCC standard method. The strains were cultured on nutrient agar and incubated for 24 hours. Treatment of cotton fabric with alum. Fabric was treated with 5% of alum. The material and liquor ratio was 1:30. The alum was dissolved in water and was kept at water bath temperature of 70 degrees Celsius. The fabric was treated for about 1 hour and dried in hot air oven. The fabrics were immersed in the 25%, 50%, 75%, and 100% concentration of ethanol extracted hibiscus rosa sinensis for 30 minutes. Hibiscus rosa sinensis for 30 minutes and padded individually in the presence of citric acid to maintain 5.5 pH. It was again immersed in the solution for another 5 minutes and repeated and squeezing process to get a wet pickup of 80% on weight of the fabric. Fourier transform infrared spectroscopy, FTIR. Test of hibiscus rosa sinensis was carried out on FTIR instrument ABB Bowman MB3000 Canada and was available in Banaraman Institute of Technology, Satyamangalam. Determination of color strength. Hibiscus rosa sinensis solution treated samples were tested in a reflectance spectrophotometer with D65 light using color eye control software interface with IBM PC. Ks is the color value which is calculated from Kubelka-Mundt equation, where K is the absorption coefficient, S is the scattering coefficient, R is the spectral reflectance of the colored samples at a wavelength of maximum absorption. Fragrance intensity test. Lifespan of a fragrance is based on the concentration of the scent and is completely based on the fragrant compounds. The hibiscus rosa sinensis treated samples were evaluated for fragrance intensity in a subjective test method wherein judges had given the rating on a 5-point Likert scale, that is 5 stands for excellent and 1 is poor. The experiment was carried out over a period of 4 weeks. GCMS. Hibiscus rosa sinensis was analyzed by using GCMS, gas chromatography and mass spectrometry. It was tested in VIT University, Chennai. India, Perkin Elmer Claris 680s US was used in the analysis and employed a fused silica column packed with Elite 5 ms and the components were separated using helium as carrier gas at a constant flow of 1 ml per minute. Result and discussion. Analysis of the spectra is done and chemical groups identified at different frequency range are shown in the table. These are the GCMS analysis.
Right, you may reach to the conclusion.
Okay, sir. Conclusion. Hibiscus rosa sinensis was characterized by spectral reflectance, FTIR, GCMS, antibacterial assay, and fragrance intensity. Hibiscus rosa sinensis powder was purified with ethanol and analyzed with GCMS and FTIR to characterize the chemical compound. GCMS analysis of hibiscus extract revealed that The 4-ethyl-2-hydrocyclopen 2-in-1 was having the lowest molecular weight with the chemical structure C7H10O2, and one of the highest molecular weight compounds was found as tritetracontan with the chemical structure C43H88. These are the references I used for the presentation, sir.
Okay, thank you, Pranita. So, have you not studied its antimicrobial activity? Pranita, you are mute. I think she is unable to hear us.
Yeah, sir, I think she's muted.
Yeah, so in between, I've seen there is one question from Mr. Vivek Sharma to Professor Apurva Das. So he is asking, as you explained filtration, needle punch over silver nanofiber coating, if we use spunless nonwoven instead of needle punch fabric, which one is better? Okay, good question. My question as well.
Sir, I guess Professor Apurva Das has left the meeting. I'll convey this question to him.
Okay, fine. So Vivek, I can try to answer a little bit on it. Maybe that needle punch fabric is much more volumetric than the spunless fabric, and it can have much more GSM than the spunless one. That may be one of the reason. And yes, you have suggested a good solution. As Wazeb sir is already there, so Wazeb ji, can you answer please?
What's the question, please, once again?
Question is, in the filtration project, if you have used the needle punch.
Yeah, Professor Das present. Yeah, okay.
What it would be if you use the spunless nonwoven, and which one is better?
Because in needle punch, I think you can control different parameters, right? Punch density and all, and overall volumes of the structure, and as the porosity. And porosity is very important because of the, porosity, this is the fastest filtration, obviously you're talking about, and fastest filtration, the filtration efficiency depends on the porosity, right? Porosity and all. So that much, I think, must be better control in needle punch operation rather than the other options.
Okay. Thank you, Wazid ji. Let me you as well as the team inform that we had developed a cartridge filter along with the spunless fabric for this TDS reduction, and it works excellent. So I think spunless also has a potential in the removal of the impurity.
Yeah, so I'm talking about the fastest filtration. That is, I think needle punch will have better efficiency because wicking property is the main phenomenon over there. But if you go for the cartridge filtration for the second stage rather, what Professor Das presented, then I think both can work together. Not an issue.
Great. Hope Vivek ji, you have got your answer. Now I think we can conclude and then end the session. Thank you very much. Thanks all the audience and the speakers. And it was really a great session. We talked various subjects, right from the filtration to renewable energy to static.
All is being recorded. अब शैलेश जी बैठ के देखेगा अगले 3 दिन के जो है ना 72 घंटे कम से कम
Mr. Chakravarti.
Yeah, I think rest of the people can mute. And
no, Mr. Chakravarti, I just wanted to thank you the wonderful way you have conducted the entire session. Really, thank you very much.
Sir.
Thank you.
Thank you,
and
sir.
Vipula has been at the backstage handling everything so very well. Thank you so much.
Yeah, thank you. Thank you, sir. Bye, everyone.
At last, I would like to thank all the speakers for successfully coming and giving us a brainstorming session. And I would also like to thank Mr. Ayan Chakrabarti sir for successfully handling the session. And now we'll have a lunch break, and post the lunch break, we have the 3 plenary sessions. So enjoy your lunch and we'll meet after the lunch.
Sure. Okay, thank you. Bye.
Thank you so much, sir. Bye-bye.
So we are closing all the breakout rooms. All 2 other sessions have been concluded. So we are closing the breakout rooms and all will be moved to the main session. And I request all the participants to be here, and please do not log out, because we will again join the session at 2 p.m.
Yeah, thanks.
Yeah, good afternoon, Manali.
Good afternoon, sir. Sir, I'm just waiting for our chair.
Yeah, the session chair was here only. Just a few minutes back, he was there.
No, it was in main room. Now we have divided into breakout rooms.
Right.
But in the breakout room, I'm unable to find out. Oh, he's joining. He's just joining. Okay, he's here.
Yeah.
So, good afternoon, everyone. Welcome to session 7, which is on textiles for advanced technology. So, for today's session, we have Chair Professor Vijay D. Kotmare, which is a professor at VJIT Mumbai, Department of Textile Manufacture. He is awarded as many awards, like award by FTA 2017, and his area of interest is chemical modification of fiber, technical textiles, and nanomaterials. Due to short time, I will not introduce furthermore. I would like to hand over the session to Professor Vijay. Before that, I just request all the speakers, please abide to their time. And if it is 25 minutes, then please keep the 5 minutes for the discussion or 3 minutes for the discussion. for the further. And I request all the participants, sorry, apart from speakers who have any questions, they can put their questions in the chat box so that we can answer that questions. So over to you, sir.
Yeah, thank you, Manali.
Thank you, sir.
Good afternoon to all of you, those who connected with us digitally to this internationally conference on textile for advanced technology. This is our session 7. I'm Dr. Gotmare here, chairing this session. I'll be chairing this session from, I think, 4:30 to 6 p.m. So we have the restricted time. And friends, we will have a 5 talk and every speaker will be given a 25 minutes. I think we'll speak on key factor and more will spend time on the discussion, maybe a question, answer and all. So we have the first speaker today, very well-known Professor Dr. Arun Kumar Patra. Good afternoon, sir.
Good afternoon.
Yeah, Dr. Patra is a professor and head of the department of Textile, Uttar Pradesh Textile Technology Institute. Dr. Patra research area lies in the area of textile coloration, functional textile, biotechnology application of textile processing, restricted substance, which is seems to be very interesting area from sustainability point of view. And the interesting part is that Dr. Patra sir is a recipient of awarded fellow of Society of Dyer and Colorist UK. I think this is a big achievement, sir. And I'm sure you will share your research area with the participant in a different way. So over to Dr. Arun Kumar Patra.
Okay, thank you, Dr. Vijay, for the nice introduction. Hope I live up to it. Can I share screen, Manali? Hello.
Oh, sorry. Sir, you can share your screen by shift.
I can share screen, right?
Yes, sir. So just press shift F5.
Shift F5, right?
Yeah.
Okay, nice. So good afternoon to all, and thanks to the organizers for having me in this session. And I'll be speaking on multifunctional finishing of cotton. And I am from UP Textile Technology Institute, as Dr. Vijay kindly introduced. And this is more popularly known as GCTI, Kanpur. Yes. That is Government Central Textile Institute. And it's a century-old institute established way back in 1914. And then we have got different years of landmark when it became GCTI and when the 4-year course started and all that. And the exclusivity with the institute is it's primarily a textile institute. Nowadays, you find engineering colleges where you have textile. Along with that, we have other streams of engineering. But ours is purely a textile institute with 4 different branches of textiles. That is textile technology, textile chemistry, textile engineering, and man-made fiber technology. And undergraduate, postgraduate, as well as PhD courses are offered here. And the institute is quite vibrant in terms of its academic and research activities. And we conduct regularly annual conferences under the name ATMP, that is Advances in Textile Materials and Process. And usually we have sizable presence of scientists and researchers from India and abroad. So with that backdrop, let me start the technical discussion. So multifunctionality in textiles is something which is now very much upcoming. And as we know that finishes as such are integral and inalienable part of textile wet processing. And till now, the concept was to have some aesthetic properties imparted to the fabric, but now people want to have multiple functionality. Say, suppose you have an anti-crease or wrinkle-free trouser, but along with that, it may have, say, some properties like, say, antimicrobial properties.
Sorry to interrupt in between. Your slides are not moving. Can you make it without slideshow? Can you present it?
Okay. So I escape. Is it visible now?
Yes, sir, it's visible now. Sorry.
Okay. So the earlier slides you could not see?
Yes, sir. Earlier slides we would
No, sir. You can start.
Okay. So that is how the functionality has changed, and now people want to have multiple effects with the same kind of finished fabric. So the major drivers in this is the cost to performance ratio. The cost should be less, but the performance should be good, and the speed of production should also be high. And that is possible when you have multiple finishing effects in a single go, and nevertheless serviceability. But the challenges are the compatibility of the components in a finished bath. Say suppose one is a cationic one and the other is anionic one, then the compatibility could be a problem. Then the contradictory effects, say one is hydrophilic, the other one is hydrophobic, then there can be a problem. And more importantly, the sustainability in terms of environmental considerations, because these days environmental considerations have become very, very important. And the traditional importance given to the quantity of production although remains, but still it's now more important to have an eco-friendly process. That is something absolutely necessary. And chemicals being an important input in the textile finishing process, the restricted substances are to be avoided. Now, among the different finishes, anti-crease finishing of cellulosics is one of the important attributes. And in fact, in this work, anti-crease finishing has been primarily aimed at. And as we know that DMDHU is mostly used for anti-crease finishing. And if you go by the structure, you've got 2 methylol groups and 2 hydroxyl groups in that, which form ether linkages with cellulose. And it gives a very high crease recovery. Even as on date, most of the anti-crease finishing agents are DMDHU based only. But gradually, it is facing a lot of restrictions. And if you see the present day RSL, that is the restricted substances list brought out by AFM, that is apparel and footwear in the international RSL group, management group, they have restricted the content of its formaldehyde. And formaldehyde, as we know that it has several disadvantages. One is when you inhale it, due to its reactivity, the formic acid and carbon dioxide had formed in the upper part of the respiratory tract. And that is something which causes serious nasal and respiratory irritation. Other than that, it also has a problem with the skin, and it causes dermatitis, which is a very known fact. So let me not dwell much into it. And the formaldehyde restrictions we have there in place from a very long time, way back in 1975. In fact, the Ministry of Trade and Industry of Japan, they first came up with these restrictions, and the fabric which are outer wear not coming in contact with the wearer's body can have up to 300 parts per million formaldehyde, whereas the ones which are in contact with the wearer's skin, it is 75 ppm, and of course for children, it's 0 ppm as the skin is very sensitive. And the FM RSL, it restricts the values to 75 ppm for adult and children, and for babies it is 16 ppm. So the only idea is to have an alternative to this formaldehyde. So polycarboxylic acids are one such viable alternative which has been worked on for quite some time by now. And BTCA, that is butane tetracarboxylic acid, is one of those chemicals. But the problem with BTCA is it's expensive and its availability is less. So these are examples of some of the polycarboxylic acids which we can use. It can be dicarboxylic, tricarboxylic, tetracarboxylic, or it can be hexacarboxylic acid. Now, just to show how it works, so if you're using malic acid, which is a dicarboxylic acid, as you can see, and here, as you see, there are 2 COH groups. So when it is reacting with cellulose hydroxyl group, it forms an ether linkage. It forms an ester linkage. So if my cursor is visible to you, is the cursor visible? Yeah, Manali, is it visible? Is my cursor visible?
Yes, I think. Yeah.
Okay, thank you. So here, if you see this entity, if you make as R and this cellulose part as R dash, then it is RCOOR dash. So that is an ester linkage. So by esterification, in fact, these polycarboxylic acids act, contrary to the DMDHU based products which work by ether linkages. Now, one more extra reaction that is possible is if you use, say, a phosphorus-based compound, then that can further react with this. And as you see here, it is a simple addition reaction. Okay, nothing is eliminated, nothing is substituted, and it is a simple addition reaction, resulting in retention of phosphorus in the total entity. Okay, so once it again further reacts, you find that it is now it is a much larger unit with phosphorus embedded. So the advantage is if you have phosphorus, then there is possibility of fire retardancy. So this way we can have multiple functionality on the fabric by using this as a catalyst. So this will catalyze the cross-linking. At the same time, this will also help to a certain extent increasing the flame retardancy. Similarly with citric acid, so citric acid, this is how it reacts. And as it shows that the citric acid here is reacting with the cellulose hydroxyl group. So here there is one reaction, again there is further reaction. So more the carboxylic acid groups, better will be the reaction. So that is an advantage if you are going for higher number of carboxylic acid groups. Okay, then besides this, the other chemicals which are used in this particular experiment is titanium dioxide. In fact, the use of titanium dioxide has broadened in last couple of years. So earlier it was mainly used as a photocatalyst, but now it is found that it has got good applications even in UV protection. And sodium hypophosphite is a catalyst which is particularly useful for polycarboxylic acid application. And other than that, because of the phosphorus retention, it can also have a significant fire retardancy. So now coming to the actual process. So the materials and methods, bleached cotton fabric was taken. And in fact, the initial trials were taken with malic acid, succinic acid, and citric acid. And all the three were first used. And sodium hypophosphite and titanium dioxide were also applied. And titanium dioxide normally has a problem of having a uniform dispersion. So Matexyl D and DLP, this is from Croda. So this was used as a dispersing agent. And by pad dry cure application, as per the table given here, the different concentrations were tried. But the problem was when these chemicals were used or tried, like malic acid, succinic acid, and even citric acid, the level of anticrease was not very high. So later on, the work was zeroed down to citric acid, and along with that other parameters, and malic acid and succinic acid were not subsequently used. But initial trials were taken with this, right? So that is what is mentioned here. And the different tests carried out were the crease recovery angle for the CRA or anti-crease effect, then fire retardancy by flammability test, then UV protection by UPF, the ultraviolet protection factor, and it was measured in ultraviolet prevention performance tester by Gester, and then the SCM analysis and whiteness, yellowness, and then tensile strength. So this is the initial trial which was taken. So here you find that the crease recovery angle is not very high. So because of that, finally, among these, the citric acid gave relatively better results. And obviously because of more number of carboxylic acid groups, as I just told you, and hence there is a possibility of higher cross-linking with the cellulose hydroxyl group. So this was the design of experiment which was followed. And there were three variables mainly: citric acid concentration, then sodium hypophosphite concentration, and TiO2 concentration. And they're labeled as A, B, C. This is important because later on when we go to the graphs, we'll see that these are useful while correlating the results. And three different levels: low, medium, high, -1, 0, 1, and the corresponding values. So these were taken And based on that, the results were like this. So the values that are mentioned there, so here they are in that coded form, and the freeze recovery angle, the UPF factor, and the fire retardancy, these are the values. So right exactly from the table, it may be a little difficult to decipher the type of trends. So we'll go to the graphs and that will make things more clear. So with this Box-Bunken design of experiments, so this was the effect on CRA. So if we see the graph here, here we find the first one where it is an interactive effect between B and C, that is the concentration of sodium hypophosphite and the concentration of TiO2. So here we find that as the SHP concentration is increasing, you can see that here there is also an increase in the freeze recovery angle. So this clearly states that with higher concentration of the catalyst, the phosphorus-based catalyst, there is an increase in the freeze recovery angle. And this is what we in fact wanted. In case of TiO2, there is not much of an improvement with freeze recovery angle, right? And here also we find that as the freeze recovery angle is increasing, there is an increase in the citric acid concentration. And TiO2 somewhere in between is quite okay. And if you see the contour plots below, you'll find that if you extrapolate, then probably if with further citric acid concentration increase, there will be a further increase in the freeze recovery angle. And coming to the third one, here the citric acid concentration again positively influences CRA and the SHP. Both these, if you combine, here also you find that it is gradually increasing. And if you see the strip, so you have the maximum CRA when you have the highest concentration of SHP and highest concentration of citric acid. So this is the interpretation, the one that I just told you. So high SHP concentration leads to high CRA, and this could be attributed to effective catalytic action of the chemical and almost no interactive effect between SHP and TiO2 concentrations, and no significant effect of TiO2 on CRA, and medium TiO2 with high SHP optimal for high freeze recovery. Then this is the CA interaction, the second one that I told you. So with increase in citric acid concentration, there is an increase in the freeze recovery angle. And coming to the third one here, you have maximum freeze recovery angle achieved with high citric acid concentration as well as high SHP concentration. The one that I just discussed, if you go to the third one here, you find the top. So here you have the maximum freeze recovery angle where the SHP concentration is highest and the concentration of citric acid is also highest. So this combination, in fact, gives you the best kind of freeze recovery angle, right? So this is the ANOVA table, and the model is significant. As the result shows, you get the p-values 0.0014, very, very small value that shows that the model is highly significant. And the lack of fit is not significant. That is what we wanted, because we didn't want any kind of lack of fit. So the model is absolutely appropriate to the experimental work that is done. So the model F value 12.98 implies that the model is significant, and the P value I've already told. And the R square value was the correlation is very high. That is why you are getting a very high R square value, that is 0.94. So the correlation between the actual experimental results and the calculated values by this experimental design, they have a very strong correlation. So that further endorses the validity of the experiments which are carried out. Now coming to UPF here, in fact, you find a linear equation. Here the quadratic equation didn't properly fit to the model. And here if I just summarize, I'd probably say that the TiO2 concentration is the lone contributing factor in terms of UPF, and that you can see here when you're increasing the TiO2 concentration, there is a significant increase in the UPF factor. Okay, so here also you can see in BC also you can see that there is a significant increase in the UPF factor as the TiO2 concentration is increasing here. So this is how it is increasing, and hence the UPF factor is also high. So this is the interpretation. And TiO2 is the lone contributor here for higher UPF. And the model is significant as the table shows. Then moving to the last one, that is the effect of flame retardancy. So here again, we find, if you go to the first one, here you find that as we are increasing SHP, that is the sodium hypophosphate concentration, the flame retardancy is significantly increasing. And for obvious reasons, because the phosphorus retention will be more if you have more of SHP, because the more of addition reaction will take place between the cellulose, which is again linked to the polycarboxylic acid, and hence the phosphorus content is high, and probably that is contributing to higher flame retardancy. And again, in citric acid and TiO2 concentration, citric acid, if you see, it doesn't have much of an influence. It has a minor influence, but doesn't have much of influence on the FR. It has certain amount of influence because the possibility of cross-linking will also increase if you have higher concentration of citric acid. So that is how it is contributing. And here also we find that with increase in SHP, there is an increase in fire retardance. So this is the interpretation, the one that I just told. So that is put in words here. So higher concentration of SHP and TiO2 together favor flame retardancy. And as such, the change in TiO2 is not significantly contributing to it. And lower SHP or sodium hypophosphate levels lower the extent of the effect. So this is the table. So here the model is significant, which automatically is calculated by the software, and again, lack of it is not significant here. So that is what we wanted. So we are getting all the three properties to a reasonable extent when they are suitably combined. I mean, when the chemicals are suitably combined. And in fact, here we didn't go for a direct pad dry QO method. We first padded and dried without having any TiO2, and then later on it was padded with TiO2. Reason being that in the initial bath when it was taken, the results were not good. And TiO2, as I told you, that the dispersion of TiO2 is a little difficult, and we had in fact taken nano TiO2. So the dispersing agent we used in sufficient quantity, and then only the padding was done. So in the first case, if you see, this is untreated, and second one is treated with malic acid, which we had taken as the initial trials. And here you find some difference. And then the third one is the citric acid treated fabric. And the fourth one, here you find citric acid along with TiO2. So presence of TiO2 to some extent is seen in this scanning electron micrograph. So that is how the differences can be physically visualized when the applications were done. Whiteness, in fact, there was some reduction in whiteness because of the citric acid treatment. As such, citric acid doesn't cause much of yellowing. The yellowing takes place only when the curing temperature is very high. If it is about 170 degrees centigrade or so, that time you find a lot of yellowing, and we also experienced it. But that is why we restricted it to 150 degrees centigrade only, and there was not much of yellowing. And barring a few cases here, you find that they're almost concordant graphs. So the whiteness was by and large retained. And the tensile strength, there was some reduction in tensile strength. This shows the untreated sample, the rest are treated samples. So there is some reduction in tensile strength, but still the reduction in tensile strength didn't harm the total strength of the material, because cotton as such, is a high strength fiber. So that much reduction is not going to actually affect its use. In fact, if you use DMDHU, the extent of reduction in strength will be much more. So now coming to conclusion, an environment-friendly multiple functional finish can be applied on cotton using citric acid, sodium hypophosphate, and titanium dioxide. Here it is written as environment-friendly because none of these chemicals are really causing any kind of harm. And the best thing is we have completely avoided any kind of formaldehyde-based anti-creasing agent. And crease resistance to a reasonable degree along with UV protection and fire retardant. So three properties are imparted in this. And this is possible by this application. And sodium hypophosphate has dual action of catalyzing the cross-linking as well as fire retardancy. And TiO2, although referred as a co-catalyst, but has primary contribution in the UV protection. And no negative influence by chemicals on one another is observed, and hence it can be called a compatible formulation. So since we were told to restrict ourselves to the time schedule, probably I have by and large done it. And this is a recent publication by me in Textile Progress. So this was mainly about the restricted substances for textiles. And the main purpose of talking on this topic was not only multifunctionality, but at the same time, the importance of restricting ourselves to chemicals which are environment friendly. So this is a 101-page document. So you can go through the September issue of Textile Progress, and the details are available with that. So thank you very much.
Thank you, Doctor. Very nice work achieving all those multifunctional activity by using multi-characteristic of the material which you use, like TiO2, SHA, and I think the crease resistant purpose. Any question from the audience, please? Anyway, Doctor, I just want to ask you, just a query, not any question.
Yeah.
If this material, if you use on dyed material, maybe a reactive dyed material, basically, or maybe a wet dyed material, that does the fading of color effect is being observed in this experiment? Or it is used on the white material only? Yeah.
It has been applied on white material, but it can be applied on dyed material because as such, there is no negative impact of any of these chemicals.
Okay.
Sodium hypophosphite is a better catalyst than say other catalysts, like say, suppose if you use monosodium phosphite. So that is a chemical which causes a fair amount of yellowing. So that doesn't happen when you're using sodium hypophosphite. So by and large, there won't be much of a difference in the color. However, since it's a strong reducing agent, there can be a minor change in color. So that is possible, but it has to be worked out and seen.
Yeah, good. Any question from the audience? Okay, good to see your work publishing in Textile Progress. That is a very upcoming area, restricted substance. And I'm sure this will help to our textile processing fraternity in the future. Manali, may I call second speaker?
Yes, sir. So second
Okay,
speaker
thank you, Dr. Gotmare.
Yeah, thank you.
Second speaker from the company has walked out, so you
Okay.
can call the IL.
Okay, yeah, thank you. Friends, we have next speaker, Dr. Priyasamy Siddhan. Dr. Priyasamy, you are there?
Sir, good evening. I'm there, sir.
Yeah. Good afternoon. Good afternoon.
Good evening. Yeah, nice.
Yeah. Priyasamy is a faculty of technology and engineering, MS University, Baroda. Priyasamy, I know you have the two important patents on your name, and you have published a book on industrial textile fiber for filtration.
Yes.
Am I right?
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Fine.
So, Priyasamy, over to you. He will be discussing on surface engineering in technical textile. That could be a innovative subject for textile technologies. Over to you.
Good evening, everyone.
Can you share your screen?
Yes. Could you see my screen?
I think you can make on presentation mode.
Yeah, I have opened my presentation. Is my screen visible?
Screen
Yes, sir, your
visible.
screen is visible.
But bring in the slideshow. Yeah. It's good.
Yeah. Okay. Thank you. Thank you, Dr. Vijay sir and the chair. And I would like to thank at this point of time the organizing members for creating this wonderful online international conference, which provides a platform for all the textile experts to present their work. And so I would be talking on surface engineering and technical textiles. This, of course, is my area in which I have done my research work. So since our time is limited, I would like to adhere to the timing. So if we see the surface modification, we have mainly mechanical and chemical and psychochemical method. At the first place, why should we look much into surface? I think we all know that any material or any substance, surface plays an important role, because that is what we see, and that is what of course interact with the another substance that is coming into contact. Therefore, surface is a very important segment. Of the three methods listed, we have, I think, many examples for mechanical and chemical, and there are their own advantages and limitations. And the physical chemical method are having some selected advantages, because one of the main advantages is that it does not use any wet method. It is a dry processing. So we have these physical chemical processes having the interest amongst various researchers, and some of the commercial scale also has come. So there are many physical chemical processes. We can just see that the corona discharge and flame treatment and so on. Of this, the gaseous plasma has a special interest. So we would discuss something about plasma science and its application in general textile as well as specific to technical textiles, covering part of our work. So as we all know that the plasma is one of the states of matter, that it is actually the fourth state of matter, which is not regularly seen on the Earth's surface. It is the ionized state of gas. So that is the basic understanding about plasma, and its composition is to be understood. The energy state of the plasma is comparatively higher, and we understand that in terms of its particle energy. And the particle energy is high, it is close to 10, and that reflects the reaction medium, the environment of the plasma. So essentially, the plasma is a fourth state of matter containing the complex species in its environment. Mainly, we have charged particles, radicals, and excited electrons and molecules, and so on. These are the complex reactive environment which are responsible for modifying the surfaces. If we look, the moment we have the plasma term, which may sound that is something beyond our reach, but some of the common examples we can come across with reference to as an example of plasma is all our everyday we see sun and lightning bolt and even hydrogen bomb, and of course the simple flame what we see in our house can be an example of plasma. So if we see these as an example, how can we apply it in textile? Can be a question. That is when we come to the understanding the categories of plasma. We can just understand that there are three. We can broadly understand that the thermal plasma and cold plasma and hybrid plasma. These three categories are understood based on mainly the temperature of the system, which can range from room temperature to over 50,000 degrees C. So that is where we classify, and the thermal plasma is essentially having a high system temperature, which cannot be used for surface modification purpose of textiles. Main point to note in thermal plasma is there will be equilibrium between the neutral particles and charged particles. That is why the total system temperature is at a higher level. The next one is the cold plasma, what we call it as the system temperature will remain at around room temperature approximately, and that is mainly because of the lack of thermal equilibrium between the charged particle and the neutral particles. And there is a hybrid plasma, or we can call it as a corona discharge, where we will have a sort of thermal plasma that is like a fire spark in the cold plasma environment, which is actually the hybrid plasma or corona discharge is referred to as. The temperature of this system can be slightly higher than the cold plasma, maximum close to 500 degrees C. So there are a number of applications of low temperature plasma. So what we will be essentially discussing, the system used for surface modification is low temperature plasma. And the low temperature plasma is not just used for surface modification of textiles or even the materials. It is used in many applications, the concept of low temperature plasma. And in fact, we have tapped that science to our textile applications. So, when we talk about why plasma radiations amongst all other dry processing techniques, like we have a gamma radiations or electron beam radiation, is mainly because when we talk about surface, we have something called bulk also. So in the name of modifying the surface, if the bulk properties are affected, then the purpose itself is lost. Therefore, one of the main considerations that the bulk property should not be affected. So the plasma, because of its nature, is limiting its modification to only to the surface. That's the main point to note. And the other thing is, of course, common to all other dry processing techniques, that it does not use wet chemicals, and even if used, it can be used in limited quantity, and therefore it is eco-friendly process. Hence, it is the interest. So when we just briefly see the principle of plasma, it is nothing but a simple discharge between two electrodes. When we look at the simple fluorescent lamp, we have electrodes, two electrodes filled with gas. When we supply electricity between the two electrodes, the gas will get discharged. So for what? For conducting the electron from one terminal to the other terminal. So the gas between the electrodes remains the plasma. So that's all. So, but what we do is that we engineer that for our purpose by changing the type of electrodes and the distance between the electrodes and the type of gas and so on. And of course, the type of supply we give and so on. I just provide about the plasma types little later. This is a simple typical setup of plasma. It can vary also. So it consists of essentially the power supply, through which we can vary the voltage or frequency, and we will have probably the step-up transformer, because plasma discharge requires slightly higher voltage than our regular voltage what we see in our day-to-day life. It can range about 5,000 or maybe 1,000. What we use in our house is 440 or 220. So we have to supply, therefore we require a step-up transformer. Of course, the other engineering aspect, like we can have rollers for passing the fabric. So coming to the type of plasmas, there are many types of plasmas there. We can classify based on the pressure. It's very important for particularly textile applications. When we have atmospheric pressure plasma, we can have the systems which can run in the open atmosphere in a continuous mode. But when we have low pressure, we need to have a closed system. That is the main differentiating factor. So people are working on the atmospheric plasma system developments, and of course it can be classified based on frequency and the other the parameters like capacitance or inductivity coupled to plasma, and there are many. So as I've discussed previously, that the plasma, the pressure, of course, this is a little detailed understanding that the pressure, if you look at the vacuum pressure, it is low pressure goes to about 0.05 to 100 torr, which is approximately 15,000 times less than the atmospheric pressure. Therefore, it is going to consume energy. So is the need of the atmospheric pressure plasma systems. And simple atmospheric plasma system, what we can see is that the corona discharge, where we have a pointed cathode and over a large plate anode, and the discharge can take place just like a water flowing from the pipe. So this is a simple example of atmospheric pressure system. And there are other systems like by changing the electrodes and the type of dielectric material and their position, we can have different types of dielectric barrier discharge atmospheric pressure systems. So it can be a cylindrical and type also. And this is the discharge pattern, the micro discharge pattern that takes place between the two electrodes. The streamer formation between the two electrodes, because of the charge potential difference, it's like a building up of, it's like a balloon bursting. Just keep on adding the pressure and then burst. Like the charge is getting built up, and then there is a micro discharge taking place. So if you see the atmospheric pressure plasma will have a sort of micro discharge like this. It may not be a continuous one, but that would suffice for the most of the time our treatment purpose. So there are systems people have developed through the models what we have I have shown before, the cylindrical type. It's like a torch. We pass the working gas in the hollow tube where there is a electrode at the tip. When the gas leaves, it will become plasma, and therefore it can be focused on any material. So just like this, this is the plasma torch working at atmospheric pressure. So this can be another model where you have passed the working gas between the two parallel electrodes, and it is discharged when it is leaving the electrodes, and therefore it will be contacting the substrates. So this is something about the type of plasmas, and whenever coming to the characterization part, we have a number of methods like surface morphology for chemistry as well as physics. So X-ray photoelectron spectroscopy is the method which gives you a very precise analysis of the change in the atomic composition at the surface. An atomic force microscope gives the very finer level change in the surface roughness. And there are other methods like ATR, FTR, and carbonyl group analysis, and simple methods like contact angle. Wetting time is the simplest method, but we can learn about the change in the surface energy. And some of the points, actually, we should be careful about the characterization of the sample preparation, because it is going to work at the surface level, to be careful. And we have to work on the, be careful about the instrument sensitivity and the sample preparation and so on. And I'm just also listing some of the global manufacturers of plasma systems like Europlasma. I think we have one presenter parallelly doing this. And Surface Technologies, Dow Corning, Linear, and Plasma Surface Technology, and so on. I'm just listing here the some of their instruments which are already available. And I would like to just say a few things about the mechanism, that is the surface plasma substrate interactions. When we see that there are physical, it can be understood in terms of physical phenomena, like it is something about etching. One of the physical change that takes place is the surface etching of the material will take place. So that is because of the plasma species and also much with the UV radiation. So this we require for most of the application, particularly we will be learning that for technical textiles. One of the successful applications is that the interfacial bonding strength improvement, particularly for composite application. This is required because if you have a smooth fiber, then the bonding of the interface will not be good. So we require some sort of surface roughness where this technique is much used. And another thing is that the chemical changes. Chemical changes, of course, again can take place because of the chain session. Radical formation will be there, and that can be used for grafting through the plasma polymerization or cross-linking, or adding some additional functional chemicals to react with it. So I was just telling you about the plasma system temperature and so on. Sometimes we have to correlate that the electron energy will range somewhere around 1 electron to 10 electron volt, and the breaking up energy of the covalent bond will be in the range of 4 to 9 electron volt. Therefore, we have to tap what kind of covalent bond we are dealing with and what kind of energy range we have to keep in the plasma. We have to map with this so that we can initiate the required chain reaction and the chemical reactions. So what is required? Relatively very high mass of ions to the top electron hinders the energy transfer from electrons. Thus, the system temperature remains neutral. This is the principle of the low temperature plasma. And because of the same chemistry, the LTP is restricted to the submicron level of the substrates. And of course, role of electrons and ions are important. So the role of electron is mainly to initiate the surface radicals and chain sessions, and the ions will decide the rate of reactions. I'm just skipping this in detail because of the time constraints. And some of the gases used there are many types. We can classify them in terms of polymerizing and non-polymerizing gases. And also we can choose the gases based on the kind of surface we want, whether we want hydrophobic type or hydrophilic type and so on. So for example, for hydrophilic type, we may use fluorine containing gases, but for hydrophilic type, we can go mainly for air because we do not have to use special gases. So one thing about the UV radiation in the plasma is something we need to understand, because as I discussed earlier, this is something to do with the etching, because particles are excited into higher energy state. When they come back, then they release the radiation, which is UV, and the UV radiation is much used for chain reaction and of course for the etching purpose. So I will just now discuss some work what we have done in the similar area in technical textile, that is a preparation of composites. So I would like to address some of the applications when we see that composite interfacial strength enhancement is one of the area which this plasma technique is something promising. And also development of coated textile for coated textile, where again the interfacial bonding between the coating material and with the substrate is again just used. And another area is medical textile. It has been much explored in medical textiles for surface engineering of the medical substrates through grafting and surface chemistry enhancement for compatibility and functionality purpose. And also for filtration, because filtration is one of the important technical textile area where we need to decide the absorption behavior of the media based on the filtration requirement. And we can actually list many more. This is a very vast area. So in one of our studies, what we have done is that we have taken the comparative study of nylon reinforcement with rubber composite making through chemical treatment as well as enzyme treatment and also with plasma. And just I am presenting a small part of it. So what we have done is that we know that the nylon is sensitive to formic acid. It is actually a solvent. So what we thought is that we just wanted to see how the nylon responds with the different concentrations and the temperature and time of the formic acid. And we have taken lower concentration and temperature and time effects. So we hoped for the strength change. So if you see that the tensile strength is the representation of the bulk properties of the material. So we have measured the surface roughness through the Kawabata using Kawabata system. We can see that there is an increase in surface roughness with an increase in the treatment effect, but also there is a tensile strength. So this is, as we expected, the chemical treatments will have an effect on the bulk property, and that is what is noted here. And we can see that this SEM shows the untreated and treated nylon with the formic acid, and this is the interfacial after the peel-off test. The coating of the rubber with the nylon fabric, and after the peel test, we have analyzed the SEM, and we see that the binding of the rubber the debris are more with the plasma treated one. So this, in this case, the formic acid treated one, because of the roughness, it helps a better binding. So this is the peel strength. We could see that the after the modification, we can see that the treated sample shows the higher peel strength value. So this we have seen, and the next one we have done was with the nylon with the enzyme treatment. We have used the protease enzyme again as which can do with the amide substance. So we can see that again there it was estimated based on the weight loss. What is the weight loss of the nylon with the treatment? And again, surface roughness also is found to increase, and we have found the optimal value of 4. So and then there is a slight decline. We see that the peel strength again it shows that with the treatment it increases, and this is the treated SEM pictures of the nylon, and the tensile strength again there is a slight decrease in this enzyme treatment, maybe because of the again same bulk effect. So the next thing what we did is with the plasma. And we can see that we have done the treatment for 15 seconds to 60 seconds, and there is an increase in the surface roughness, and the weight loss is very low because the plasma is restricted to the surface only. This is the plasma treated nylon samples, and the tensile strength we see here also a slight decrease is there, but not much. So it is coming down to 292 and 290 only at the 15 seconds. And with 60 seconds, we see slightly lower value. So the peel strength is also, we can see that there is an increase in the peel strength. And it is found that at 30 seconds, even the peeling was difficult. It could not be peeled. So there is a notable increase in the peel strength. This shows that the binding between the matrix and the reinforcement is improved because of the surface toughness. And of course, in all the three techniques, so the inference is that all the three methods have yielded higher field strength, indicating the higher interfacial adhesion, and that is, as we discussed, because of the increase in the surface roughness. Of the three methods, plasma treatment has given a high field strength to an extent that before the failure of the interface, the material itself fails and it does not affect the bulk compared to the other techniques. So thank you, and this is what I just wanted to share in this forum.
Thank you, Doctor. This is a nice presentation, and you touch upon the process of environment friendly again by using the plasma technique. Very interesting to see the hybrid plasma application there also. I'm sure the audience would have taken this subject, maybe their future research. Any question from audience, please? Miss Manali?
Yes, sir. There is no
Audience,
question in the chat.
audience, they can
box.
ask question, they can mute and unmute.
Yeah, they can unmute.
Yeah.
And if they have a question in between, they can write a question in between.
Sir, good evening, sir. I just wanted to know probable applications of these specific things. Means, is it possible to think that we can replace the conventional water usage or something like that within the next 5 years or 10 years? Or how do you feel when this will be industry ready? The technology.
Yes, sir. Yes, actually, one of the challenges we have is that how to have a continuous. There are two challenges in the plasma treatment. One is that a continuous running system, that is atmospheric plasma system. And as I discussed, there are uniformity problem is there. Another thing is that what we see is that because the treatment is restricted to only surface, there is a aging effect. So after about some time, the surface chemicals can go. So except the applications like interfacial bonding or due to the mechanical surface roughness, there are some challenges. If we can fix that, I think this can come up.
Doctor, I think you have touched upon the work on surface modification on nylon.
Yes, sir. Yes, sir.
As we have seen that nylon material have very less uses as in the apparel area.
Yes, yes.
But if you can modify the surface and enhance certain moisture over there, perhaps it may have some application. So you have seen, I think somewhere I also seen your work, the enzyme treatment. So,
yes,
correct. So how you'll find this enzyme treatment is effective from commercial point of view?
Oh, the excimer treatment. Okay.
Yeah.
Yeah, actually, that is a very interesting. I have not touched here in this work. Excimer is an alternative to the plasma system because that works based on the UV radiation, and that actually solves the atmospheric pressure requirement of the plasma system because it works at the atmospheric pressure. But only thing is in that there are two constraints. Is that again the aging effect is still remaining as a problem to that technique also. Another thing is that it generates huge ozone, and the ozone system has to be handled carefully.
Yes.
So these are the things.
Yeah. So certain challenges are there.
Yeah.
Good, but the research can be on this area in the future. Fine. So we have now the next speaker, Mr. Shiva Jagdish Kumar Mungala. Sir is from Vignan's Foundation for Science, Technology and Research, I think Vadlamudi.
Yes, sir.
Yeah. And sir, we're going to speak on very interesting topic. It is again touching to the environmental base activity, the effect of bio-based phase change material application to the comfort properties of Indian fabric.
Sir, I think I am unable to.
Yeah.
I am unable to share the screen as. Teresa, sir, can you stop screen share?
Yeah. I'm stopping that.
You can take help of
Yeah.
Host, can you help them to share their screen?
I've stopped it.
Dr. Teresa is screen to discontinue.
Okay.
Yeah.
or stop. Yeah.
So, good evening. Yes.
Good.
And the dignitaries present. Myself, Srijagadish Master. Myself and Ramesh Naidu and C. Johan, who is working in interior design of NFP. We are working in this small project. So, as face changing material is also as like the plasma, it is also there in the conventional past 2 decades research revenue. So here we found one commercial application. I just explained to you, sir.
Yeah, good.
So before that, some of the basics like the clothing comfort. So clothing selection, which is one of the important thing, and which is a requirement for every individual. And also, with the progress of science, there is a big improvement in the quality of life. So, which leads to more expectations of users in terms of comfort in that. Comfort can be defined as which should be aesthetically looks good, appearance wise, and it should be accepted by the society, and at the same time, it should have protection also to the various problems. Social status and all means like it should have the appearance and it should be accepted like luster, sheen, or for specific application, specific texture, which is there, the summer wear, active wear, and specific robes, colors, all these things also. But the various types of comfort which are related to these things are like, apart from the color, those are thermophysiological comfort, health comfort, and psychological. So the confidence level of the person who is wearing, maybe the person who is talking it. So in this, the thermophysiological comfort is the one which is very much important with respect to this present topic. So, and also the comfort is defined as the absence of perceived pain and discomfort. It is perceived as, it is defined as the absence of perceived pain and discomfort. There should not be any discomfort, there should not be any pain. This is required as comfort. The clothing comfort is a state of satisfaction which is indicating physiologically, psychologically, and physical balance. So the clothing comfort is very complex and which is subjective to the perception. The person, if maybe A person is feeling it as a comfort, whereas the B person may not be feeling it as a comfort. So it comes with the subjective perception and which relates to the interactions between the fabrics, climate, human psychological and physiological variables. Some people like the body temperatures have little comfort, means more like while sleeping also somebody may like blanket and somebody may not blanket at the same temperature. So the comfort is there should not be any pain or there should not be any discomfort. So sometimes what happens is certain people are very much adjusted to very specific temperatures. So in generally, it is like physiological comfort. Thermophysiological comfort is concerned with the heat balance of the body. Basically, the 37.1 degrees centigrade of the body, which needs to be maintained. So that is the reason we generally have the problem of sweating, or sometimes people will shiver to produce for heat. That is the basic, the first instance of the body. Then physiological comfort, psychological comfort means it's all about being at peace with ourselves. So do I look good in this one? How it is? How I'm going to, means the emotional integrity. This is the second. then the sensorial. Because the psychological comfort, we may not be able to change much. It depends upon the ingredients. But whereas the physiological comfort and the sensorial comfort is also important for the parking operations. So out of this, in order to improve the thermal comfort, thermophysiologically can improve by means of selection of proper fabric constructions. That can be either changing by the cover factor or DSM of the fabric, or what you call the proper finish on the surface, or even sometimes even operations like singeing, where the burning out of protruded fibers also will hamper or alter thermal. And also it mainly depends upon the type of fiber also. Like the wool fabrics which have different scents with very cold countries and all, or with cold regions and all, the wool will absorb moisture and release the latent heat. And in some cases, the air permeability is more important. And some places, whereas like sportswear and all, the wicking is more important. So these are the three major areas which related to this. So in way, means like thermophysiological comfort is nowadays coming as a material technology. So there are various types of coatings which can be used. Means certain research and all is already done. And whereas the objective of this PCM is it is capable of absorbing the latent heat. It is capable of absorbing the latent heat and by means of coating materials which are able to transfer the moisture vapor and the liquid. Like Gore-Tex is one of the example, which is trademarked fabric and which is there in the industry past almost like 10-15 years. Then PCM materials are sometimes even some patented technologies with Nike and Adidas also to have certain slits in the gap, so that the ventilation in those specific areas, especially in few of the things, and also a panel technology. The T-shirt consists of different types of fabrics at different panels. Under the arms, there is a different kind of fiber construction which is being used. So there are various technologies which come under the material. So one of the technology which is PCA, even though we know it, but it is not being much commercialized as of now. So PCM is a phase changing material. So it will change its phase from liquid to solid state at a gel state basically. So it is a substance which releases or absorbs the material, releases or absorbs the energy from the heat, and the phase will be transitioned to provide the useful heating or cooling. So when the heat is more, the phase change material will take the heat and then which will make the ambient temperature or required. Similarly, either from the heating or from the cooling, the heat will be stored in the phase changing materials. Generally, these are available with respect to paraffin waxes and non-paraffin organics and hydrated salts and some of the metallics. So commercially, they are available between 5 degrees to 73 degrees centigrade. 5 degrees to 73 degrees centigrade. Just show you one of the material which we have selected, which is made from protein. So it is having the range of 5 degrees to 74 degrees centigrade. So 5 degrees, 6.5 degree, 9.5 degree, 15, 19, 21. These are the cold temperature, ambient temperature, high temperature. And just believe it where it will be used. Say for the 5 degrees, 6.5 degree, and 9.5 degree, as the phase changing materials, basically to protect the sensible goods or sensitive goods during shipping in a long time, like cold and full temperature combination. Slowly it releases the saved temperature. And similarly, the cold storage applications in order to cooling some of the spaces, refrigeration and food keeping to keep the sensitive goods cold when the electricity is unavailable, or to reduce compressor on or off. Even nowadays, even if you order some chocolates online also, during the shipping it may melt it. So what happens? Some of the ice pack will come along with it, or along with the medicines also sometimes. And ice packs. These are the phase changing material is a simple example of an ice pack. So even for the consumer applications, generally for the 15 to 37, for most of the temperatures, building constructions, ventilations, along with the ACs also nowadays, these sort of ice packs will be there. So which will absorb whenever the compressor is running at a higher speed, it will absorb the heat and slowly it will releases. So thermal energy storage. I mean, nowadays even the applications are coming into mobile phones also. So when the processor works at a very high temperature, so what it will do? Immediately the processor or the semiconductor devices may fail from its surface. So the higher applications like 53 degrees, 60 degrees, 74 degrees, in order to save the electronic circuits from the mobile applications or computers or any of the hard disks or the data storage devices or Amazon web servers, in those cases, and these will be used. So these are some of the normal applications. Whereas the phase changing materials, which are successfully already installed. So in this, so which type of PCMs is selected based on the climate is like for cold climate with low activity, it is required to retain the heat by using the insulated material. And for the hot atmosphere with more activity, it is required to dissipate the heat. You need to dissipate the heat very fastly, as like a sports wears, the ones which are purely made from the 100% polyester fabrics with high wicking capacity to avoid the hyperthermia. Otherwise, what will happen? The temperature of the body is keep on increasing, and the sweating will be keep on increasing, and then after some time, the people may not be able to what happens is still keep on. The temperature will be slowly, means suddenly it will change. That is known as hyperthermia. So more permeable fabrics and will improve it. But for the garment where it is required to cover the garment with less permeable or impermeable material, or in certain cases like tropical conditions, we cannot use both these conditions. Whereas PCMs will be very much helpful for us, okay, in these specific applications. So these can be used in the form of coating to provide a thermal comfort by absorbing the heat released by the body. That is what we have done, sir, here, Vijay sir. So it is basically done with either micro encapsulate technique or padding angle or spraying, or by keeping the ice packs or these things in the pocket. The pockets application is the simple application, but it will create a lot of discomfort. And so here we have gone with the coating technique. We have selected a proper binder, and commercially available, the bio or like the product which is commercially available, but not for the textiles. We have taken that into the thing, and we have added with the proper binder, and then we have tested the fabric for how it is functioning. So this is some of the earlier works there. So it was found that around 6.5 watts decrease in heat lost for the body of a single layer, and 13.2 watt for the double layer by PCM coating fabric compared with the uncoating. Means there is a latent heat of around up to 13 watt is available in the earlier research center. But in our research at present, the one which I am going to show is we received up to 40 watts, 40 watt differences. So, like in some of the work and like which is earlier, which is there, like 12 minutes, and by keeping the pockets I like ice packs and all, 40 to 55 watt per meter square is achievable. But here with the coating, we were able to do it. So this is the general heat produced from the body. This is all like how much voltage and what is per meter square, the heat of production during sleeping, during resting, during sitting, typing, and slow walking and fast walking, how much it is the rate of heat production. So scope of PCM, I'll speak it, I'm touching so much. Here, what we have done, we have taken 3 different types of fabrics. So with fill wave and plain wave, and with plain wave also with 65 GSM and 46 GSM. And we have taken the Prodatherm 29 as the standard, whereas the maximum heat absorption will be taken place at 29 degrees. And then we have studied with different PCM and binder combinations with 90% PCM and 10% binder, 50% PCM and 50% binder, and 100% 0%, like that. All 9 samples were taken. So these 9 samples were coated. So the before weight and the after weight, which are being shown here, around 20% of the extra added we have taken, which consists of both testing material and also the suitable binder. Then these applications we are finding in automotive textiles, active wears, lifestyle apparels, even for the gym wear also, or outdoor sports, even for the aerospace textiles and medical textiles also, wherever temperature person who has got a fever. Okay, so basically what happens is due to more heat which is it acts as insulation. So by having a specific these kind of PCM applied fabrics, so what happens? Only the required temperature it will absorb. It will not even means it will not reduce too much of the person's body heat. So majorly we have tested these fabrics with respect to their permeability, stiffness, and heat absorption. Stiffness wise, there is a slight increase in all the samples. And like PCM, we have got with heat absorption is around 40 milliwatts. And you see, since we have selected at 29, Prodatherm 29, which is available. So at 30 degrees Celsius, the maximum heat absorption is DSC.
Sir, we have the time limit. So
yeah, I just closing.
Yeah. We have the one more speaker. Yeah.
Yes, sir. Yeah. So the air permeability, since the airs are the area is getting blocked, so certain reduction in the air permeability and we observe. So basically, from this, what we can use this PCM, we are even in some of the negotiation and some of the trials with the commercial application on the knitted fabrics as well, from the NFT side and from the retail side also. So these PCMs can be used in the active wear and other applications. And since it is a biosoluble agent and there is no irritations or no rashes on the skin and other things. So these can be suitably used for the knitted fabric application. These are some of the references in this area. And
nice, very good collaborative work. And as you are saying, there is a global warming on the earth, and there's a definitely rise in temperature.
Yes, sir. Yes, sir.
People will need of this phase change material in the future.
Yes, sir.
To see how economically we can develop this thing, so common man can utilize.
Yes,
yeah.
Yes.
Any question from the audience, please?
So in the chat box, there is no question.
I think, shall we go for next speaker then?
Okay, sir.
Yeah. Okay.
Okay, sir. Thank you.
Thank you, sir. Good work. Best wishes to you for your future research. We have the next speaker, I think Stuti Srivas. Are you there?
Sir.
Yeah, good. Dr. Stuti Srivas, she's from Rajiv Gandhi Institute of Petroleum Technology, Amethi. And she's on very interesting topic regarding energy storage I think the entire world is fighting for that. Okay, and she's speaking on carbon nanomaterial from natural fiber for energy storage. So, Dr. Shruti, please start your presentation. Thank you.
Sir, sorry to interrupt you. I am PhD scholar now. I am not doctor till now.
Okay, and it is screen it came anyway. All the best to you. You would be
Yes.
very soon. Yeah, good.
Yes.
Please start. You can share your screen.
Yes, sir.
Yeah. We have 10 minutes as per schedule and touch upon your research concept and its application.
Sir, my slide is visible?
Not yet. Manali, can you help her?
You have to share your screen. In the icon, you have share screen option. Top down, there are icons. Yeah, now.
And now
Yeah.
is it visible?
Yes, it's visible.
Good evening to all the committee member. I am Stuti Srivas, PhD scholar from Rajiv Gandhi Institute of Petroleum Technology, JS Amethi. Today, I am discuss about how to develop a carbon nanomaterial from natural fiber for energy storage. In introduction part, due to the depletion of conventional sources, the need for to develop energy storage device from renewable sources increases. Natural fiber are renewable resource to develop carbon nanotube or carbon nanomaterial due to its abundance and low cost. So, what is natural fiber? Natural fibers are the fibers that is obtained from plant and animal sources. It is divided into two types based on their source, plant-based and animal-based. Like animal fibers are wool and silk, and plant fiber are cotton, coconut coir, and jute. Uh, Plant fiber consist of have some composition like natural fiber have some composition. That composition consists of lignocellulose. After chemical pretreatment in pictorial representation, uh, plant cell plant cell wall or plant fiber consists of lignocellulose, and after chemical pretreatment it is further divided into cellulose, hemicellulose, and lignin. After knowing the composition, like here, lignin has more carbon element than cellulose and hemicellulose. Cellulose has high crystallinity, and hemicellulose degrade fast at low temperature by using diluted acid or base compared to other. After knowing fiber composition, selection of precursor is important because it affects the carbon yield and structural characteristics. So what is precursor? Basically, precursor is the plant source that has a potential to convert into carbon powder with elemental and chemical composition. So the selection of precursor is important because if we select a good precursor, then it affect the carbon yield, and it affect the structural characteristics, which is important for making energy storage device from carbon nanomaterial. And the in precursor, if we have the presence of nitrogen and oxygen content, then it affect the conductivity and capacitance also. For making it compatible for energy storage device, fiber should rich in nitrogen as well as lignin content. If we take a natural fiber precursor, then it is converted into carbon derivative like carbon nanomaterial or carbon nanotube. Then further, this carbon nanotube is used to make a energy storage device that have a high power density or that is having a green energy application. Like for developing the for selection of precursor, after selection of precursor, there should be different synthesis method is used to develop a carbon nanomaterial from that fiber natural fiber precursor. So there are different type of synthesis method like hydrothermal carbonization, chemical vapor deposition, pyrolysis, physical activation, and chemical activation. In this, I give more emphasis on pyrolysis. So what is pyrolysis? The pyrolysis is a thermal cracking of its macromolecule, then releasing its condensable and non-condensable volatiles residue obtained is biochar. So in biochar, the product obtained after the pyrolysis of natural fiber. The biochar is the biochar after getting a biochar product. That biochar yield determine the elemental composition and chemical structure. This will determine is it compatible or is it having the high yield to make a carbon storage, carbon based energy storage application or not. So only I have taken a pyrolysis synthesis method in which biocharing is the most important process. After biocharing a natural fiber, then we make a carbon nanotube by that biochar product. Like if we take a natural fiber, for example jute, then biocharing process was performed without any pre-treatment while conditions were in control to achieve carbon nano or microtube. For silk cocoon, the biocharing was performed and further oxidation and reduction performed to generate nitrogen doped graphene. And if we take a cotton fiber, then nanocellulose of cotton fiber is prepared by treating it with aqueous sodium hydroxide solution to eliminate lignin and hemicellulose part. I already discussed how to eliminate lignin, hemicellulose, and cellulose. Cellulose, that cellulose is then again exposed to acid hydrolysis to attain nanocellulose. That nanocellulose is characterized by chemical analysis like XRD or SEM to demonstrate its chemical structure and morphology. So after chemical analysis, it was found that the shape of rod type of structure is formed in which surface area is increased. It determined the possibility to produce CNT. So after producing a CNT from natural fiber, we will develop a energy storage device. In this architecture of supercapacitor device is seen in which if we take a nanocellulose part of cotton fiber or any natural fiber, then it is after taking it the carbon nanotube is formed by taking a nanocellulose of natural fiber. That nanocellulose is mixed with carbon nanotube composite film that both are mixed, and then if it is separated by a separator, and separator is sandwiched between a cellulose CNT and CNT composite film and the current collector. This separator is again sandwiched in current collector. Then the architecture of capacitor device is formed. And this, if after the fabrication of supercapacitor device, we can use for energy storage purpose. Like in this, I made a supercapacitor device using the cellulose, CNT, and CNT composite. I already discussed about how to make CNT from the nanocellulose. And after making a supercapacitor device, it will store the energy and it can use to glow the LED or any small device. And if we make a supercapacitor, then supercapacitor is also differentiate into different type of supercapacitor. Like there are two type of supercapacitor: electrical double layer capacitor and pseudo capacitor. In electrical double layer capacitor, two electrode is immersed in electrolyte separated by a dielectric, but in pseudo capacitor, two electrodes are separated by a separator using an electrolyte solution. So the energy in the storage system is stored on the surface of CNT electrode, while pore size promotes its transport and storage of the charge. And the surface chemistry and the microstructure of CNT can be arranged easily in different forms, thus transforming the electrochemical performance of the material. In energy storage device, if we make an energy storage device from carbon CNT or carbon nanomaterial, and that carbon nanomaterial is developed by using a natural fiber, then there are some properties which enhance the performance of energy storage device. Like in supercapacitor, there should be a high power density and low energy density. High stability should be there. Heteroatom doping should be there, like nitrogen and oxygen doping should be there to increase the performance and conductivity of the energy storage device. High specific surface area should be there, and pore size distribution should be there. These all properties increase the performance of energy storage device. And there are some challenges also if we make a energy storage device from carbon nanomaterial. Like for the fabrication of carbon electrode, high increase in pore structure lead to poor conductivity. This is the main challenge to overcome if we make a energy storage device from carbon nanomaterial. To obtain a better performance, the material should have mesoporosity to increase its electrochemical characteristics, and there are some functional group a role is also playing in the picture, like nitrogen and oxygen. There are different properties enhanced by using all these uh, functional groups for improving the performance of energy storage device. In conclusion, I will say that natural fiber derived carbon has improved over the past few years, but more improvement are still needed for determining their full potential for high performance of energy storage device. Like if we take a biochar product or activated biochar from the fiber, then this is the potential candidate for use as electrode for various energy application. Capacitive performance of supercapacitor is not only limited to surface area but depend on other factors also, like pore size distribution, structure, and electrical conductivity. So I conclude that there are other challenges to be overcome in this area, so we can increase the performance of energy storage device that is developed from using a natural fiber source. Thank you, all of you.
Yeah, good efforts choosing natural sources to make energy storage devices. And I'm sure, I think in the coming time, this kind of devices will be very well accepted by the society. Any question from audience?
So till now, there is no question in the chat box. Anyone who want to ask can unmute themselves and ask the question.
So all the audience, even if you have any question generated later on after listening these lectures, you can communicate them. I think the Manari will help you to get their email and all. But your question should be definitely get some clearance from speaker. Okay, because those will help you in developing your own research in coming time. I think we don't expect any question from the audience now. Anyone is there still? We have a time, 1 minute. Okay, fine. So I think all the speakers, they have really touched upon to their research area, and most of the research area is very close to the sustainability concept, environment friendly concept. I think these are the research what we going to work in the near future. I am very much thankful to the conference president, Mr. Vikas Shashra, organizing chairperson and co-chairperson Shri Kamal Mishra ji for giving me this honor. And thanks to Ms. Manali, who was coordinating with me last week about this e-conference to chair the session. And best wishes to all of you for your new research area. All the best. Thank you.
On behalf of the conference, I would like to thank all the speakers for giving such a nice talks. And I would like to thank our chairperson, Dr. Vijay Gutmari, for chairing this session so well and complete it on time. Thank you, sir. I hope some of the lectures are remaining, so all the participants can join in that session.
Yes, this session is still going on that side.
Yeah, so we will rejoin by tomorrow. Tomorrow we'll get another sessions morning, 9 o'clock. So I'll hope all the participants would be present there for the next sessions.
Yeah.
Thank you. Good
Thank
evening,
you.
everyone.
Thanks. Thanks to all once again. Yeah.
Thank you, sir.
Bye-bye.